Hello there, and welcome to Physics with William, where curiosity gets comfortable, the universe lowers its voice a little, and science takes the long, quiet road towards sleep. Tonight, we are drifting into a story that begins beneath the fields and roads near Geneva, in a place where protons are sent rushing through underground tunnels at almost the speed of light, where enormous detectors wait in the dark like patient metal cathedrals, and where, every so often, nature seems to leave behind a clue that does not quite fit the rulebook. This is not a story about a giant explosion in the sky, or a new planet appearing beyond Neptune, or a telescope finding a strange flicker at the edge of the observable universe. It is much smaller than that, almost absurdly smaller. It is a story about tiny particles called mesons, which appear for just a brief moment before they vanish into other particles. They are born in the debris of high-energy collisions, live for a fraction of a second, and then decay. Most of the time, they decay in ways that physicists expect. Most of the time, they follow the mathematical instructions of the Standard Model, the great working manual of particle physics. But in certain measurements, over many years, some of these particles have seemed to lean in an unexpected direction, as though one page of that manual might have a sentence missing. The phrase sounds dramatic, almost too dramatic for a calm evening. CERN just detected an event nobody can explain. It has the feeling of a locked door, a late-night alarm, a scientist slowly removing their glasses and whispering that cannot be right. But the real story is quieter, stranger, and in some ways more interesting. It is not simply one event, not one lonely particle misbehaving in the dark. It is a pattern of small tensions, small differences, small persistent hints in the behavior of particles that should, according to our best theory, treat certain members of the particle family almost the same. And yet, when physicists look closely enough, patiently enough, and with enough statistics to make even a spreadsheet feel sleepy, some results have appeared to whisper that nature may not be treating them quite equally. The particles at the centre of this mystery are connected to something called lepton universality. That name sounds like it should belong to a quiet department in a very large university, perhaps with old wooden doors and a coffee machine that has not worked properly since the late 1980s. But the idea itself is simple enough to hold gently in the mind. Leptons are a family of particles. The electron is one of them. The muon is another. The tau is a heavier cousin, the one who arrives late, eats more, and leaves the room before anyone has fully understood what happened. In the Standard Model, when the weak force interacts with these charged leptons, it should treat them in essentially the same way, once their different masses are properly taken into account. It should not have a favourite. It should not look at an electron and a muon and quietly choose one over the other. And that is what makes the meson puzzle so intriguing. Some mesons can decay into final states involving electrons, others can decay into final states involving muons. According to the Standard Model, after careful corrections, certain rates should line up in a very particular way. Not perfectly in every casual sense, because the universe always includes details, backgrounds, detector effects, and the kind of careful corrections that keep physicists awake long after ordinary bedtime. But the central expectation is clear. Electrons and muons should appear with a kind of fairness built into the theory. If they do not, if one appears more often or less often than expected, then something may be nudging the process from behind the curtain. Now, before we get carried away and start ordering a welcome banner for new physics, we should be gentle with the truth. Particle physics is a field that has learned patience the hard way. A strange bump in the data can fade with more measurements. A surprising difference can turn out to be a detector effect, a background process, or a subtle detail in the analysis that was not fully tamed at first. The history of science is full of little glimmers that looked like doorways, and later turned out to be reflections on the glass. Some of the earlier hints involving rare meson decays to electrons and muons have become less dramatic as improved analyses were performed. That does not make the story less fascinating, in fact it makes it more human, more. Science does not move by shouting that the universe is broken every time a graph looks unusual. It moves by asking, again and again, are we sure? And still, the broader flavor puzzle has not simply gone away. Other measurements involving mesons, especially those that include tau leptons in the final story, have continued to show tensions with expectation. Not enough to declare a discovery, not enough to rewrite every textbook, but enough to keep physicists looking closely. Enough to fill seminars, papers, conferences, and long conversations near coffee machines where someone points at a plot and says, very calmly, this is interesting. And in particle physics, that phrase, this is interesting, can sometimes be the first quiet footstep of a revolution. So tonight we're going to follow that footstep, slowly, carefully, and without rushing towards certainty before the evidence is ready. We're going to wander through the world of mesons, beauty quarks, rare decays, and lepton universality. We will visit the LHCb experiment, one of the great detectors at the Large Hadron Collider, designed not mainly to smash particles and look for the biggest possible new object, but to study what happens in delicate, fleeting decays. It is the kind of experiment that listens for imbalance, not a roar, but a change in tone, not a thunderclap, but a violin string slightly out of tune, and perhaps that is what makes this mystery so suitable for a quiet night. At first, particle physics can feel like a place of violence. Protons collide, energy erupts, detectors flash with tracks and showers and signals. But behind all that intensity, the work is surprisingly patient. Physicists spend years studying tiny differences, checking calibrations, comparing control samples, correcting for what the detector sees easily and what it sees with difficulty. They do not simply wait for the universe to shout. Very often they wait for it to hesitate. Have you ever noticed a pattern that seemed too small to matter at first but stayed in your mind anyway? Maybe a sound in the house that only happens at night. Maybe a clock that loses just a little time each day. Maybe a friend who says they are fine, but in a tone that suggests there is more to the story. Most mysteries do not begin with certainty. They begin with a mismatch between what we expected and what we actually found. Particle physics is no different. A detector records many events. Most are ordinary, some are messy, a few are rare. And in the rarest corners, where the standard model makes precise predictions, a tiny mismatch can become a question with enormous consequences. So let me ask you, before we go farther beneath the surface of the world, where are you listening from tonight? Are you somewhere late and quiet, with the lights low and the day finally loosening its grip? Are you listening in bed, on a sofa, at a desk, or perhaps during one of those oddly peaceful hours when the rest of the world seems to have gone offline? And if you happen to know, what time is it where you are? It feels fitting to ask, because CERN itself is a place built around time in its most exact form. Particles arrive in bunches, detectors measure signals with astonishing precision. Events are reconstructed from traces that last less than an eye blink. And yet the questions they raise can stay with us for decades. If you find this journey soothing, or if you enjoy the strange comfort of learning about the deepest machinery of nature, while your own thoughts begin to slow, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this quiet little corner of science reach other curious minds, including those who like their particle physics served gently, without sudden noises, and preferably with the emotional intensity of a warm blanket. And of course, if tonight's mystery keeps you awake, I can only apologize in the traditional scientific way by offering even more questions. Now let us settle into the story. To understand why these meson anomalies matter, it helps to remember just how successful the standard model has been. This theory is not a vague sketch. It is one of the most precise scientific frameworks ever built. It describes the known elementary particles and the forces that act between them, apart from gravity. It predicted particles before they were found. It survived decades of experimental tests. It gave physicists a structure so reliable that when something appears not to fit, the first response is not excitement, but suspicion. The standard model has earned that respect. If you think it is wrong, you'd better bring very clean data, and yet everyone knows the standard model is not the final answer. It does not explain dark matter, even though galaxies behave as if some invisible mass is helping hold them together. It does not include gravity in the same quantum language as the other forces. It does not explain why particles have the masses they do. It does not tell us why matter survived over antimatter in the early universe. It works beautifully, but it also leaves deep questions untouched, a little like a brilliantly organised library with several locked rooms nobody can open. That is why anomalies are so precious. They are not proof by themselves. They are not discoveries simply because they are surprising, but they are places where the wall may be thinner. If new physics exists, it may not appear as an obvious new particle produced directly in a collider. It may appear indirectly, as a slight change in how known particles decay. Imagine trying to learn that a person has walked through a room after they have already left. You might not see them directly. But a chair has moved. A curtain is shifting. There is a faint warmth near the doorway. Rare particle decays can work in a similar way. A new particle may be too heavy or too hidden to appear directly, but its influence might still alter the probabilities of known processes. B mesons are especially useful for this kind of search because they contain beauty quarks. Beauty quarks are heavy, unstable, and rich in possible decay pathways. They are like tiny laboratories for studying how particles change flavour, meaning how one type of quark transforms into another. In the standard model, some of these transformations are rare, not because they are impossible, but because they happen only through more complicated quantum processes. Rare processes are valuable, because they leave less room for ordinary noise. If a new hidden particle or force contributes, even faintly, the effect may stand out more clearly there than in a common decay that happens all the time. That is where LHCb comes in. The name stands for Large Hadron Collider Beauty. It is one of the major experiments at CERN, but it has its own personality. If ATLAS and CMS are broad discovery machines, built to look in many directions at once, LHCb is more specialised. It watches closely for particles containing beauty quarks and charm quarks, studying how they decay and whether matter and antimatter behave in slightly different ways. It is not shaped like the giant barrels many people imagine when they think of particle detectors. It is more like a forward-looking instrument, arranged to catch the sprays of particles that emerge in one preferred direction after proton collisions. It is, in its own way, a patient observer of fleeting departures. The events themselves are not seen directly in the ordinary sense. No one watches a B meson with their eyes. There is no tiny glowing bead on a screen politely labelled mystery particle. Instead, the detector records tracks, energies, impact points, flashes of light, and signals from layers of specialised equipment. Computers reconstruct what likely happened, like investigators rebuilding a brief and chaotic scene from footprints, broken glass, and a few grains of dust. From these traces, physicists infer which particles were produced, how they travelled, and what they decayed into. The challenge is enormous because the differences being studied are subtle. Electrons and muons do not leave identical signatures in a detector. Electrons are light, easily disturbed, and prone to radiating energy as they pass through material. Muons are heavier and more penetrating, often sailing through layers of detector material with a kind of quiet confidence. Comparing decay rates involving electrons and muons is therefore not as simple as counting one pile and then counting another. It requires careful corrections, control measurements, and repeated checks to make sure that the detector itself is not creating the appearance of difference. This is one reason the story has evolved over time. Earlier measurements of certain rare B meson decays suggested a possible violation of lepton universality. Later, with more comprehensive analysis and improved control of backgrounds, some of those particular tensions became consistent with the standard model. That may sound disappointing if one is hoping for a dramatic crack in reality, but it is actually science doing exactly what it is supposed to do. A hint appears, the community investigates, the analysis improves, the result either strengthens or softens. The universe is not obliged to make its secrets easy. But alongside those softened hints, other B-meson puzzles remain. Measurements involving decays to 2 leptons continue to draw attention because they appear, in combination, to sit away from standard model expectations. The tau is much heavier than the electron or muon, which makes these decays harder to study, but also potentially more revealing. Some proposed new physics models naturally prefer heavier generations of particles. If nature has a hidden interaction that speaks more strongly to taus, or to particular combinations of quarks and leptons, then B-meson decays might be exactly where the first signs would show. The possible explanations have names that sound as if they wandered out of a speculative physics dream. Leptoquarks, hypothetical particles that connect quarks and leptons directly. Z-prime bosons, possible heavier cousins of known force-carrying particles. Hidden forces that interact only faintly with ordinary matter. Connections to dark matter sectors, where unseen particles might leave traces not by appearing in the detector, but by influencing what ordinary particles are allowed to do. These ideas are not guesses pulled from thin air. They are mathematical possibilities explored because they could explain patterns that the standard model does not naturally produce. But they are not confirmed. They remain suspects, not culprits. That distinction matters. A good mystery should not confuse possibility with proof. Tonight's journey is not about claiming that CERN has already found a new force or discovered the particle that explains everything. It has not. The more careful truth is that particle physicists have found and continue to investigate tensions in the behaviour of certain B-meson decays. Some have faded, some remain. Some new measurements tighten the space where new physics could hide. Others sharpen the puzzle. The overall picture is not a clean announcement with a ribbon around it. It is more like a map with several faint marks circled in pencil, and that is often how real discovery begins, not with a single perfect answer, but with a persistent discomfort. A place where the known theory works almost everywhere, yet not quite everywhere. A result that refuses to become either fully ordinary or fully extraordinary. A measurement that says perhaps there is nothing here, but perhaps you should look again. There is something quietly beautiful about that. We live in a universe where the smallest particles can carry the largest questions. A B-meson appears and disappears almost instantly. And yet in that tiny decay there may be a clue about the deeper structure of nature. The electron and the muon, so similar in some ways and so different in mass, may be telling us whether the forces of the universe are as impartial as we thought. The tau, heavy and difficult, may be pointing toward interactions we have not yet learned to name. And beneath it all, the standard model stands, strong and elegant but not complete, like a magnificent old bridge leading into fog. So as we begin, keep this image in mind. Beneath the ground, protons circle, detectors wait. Millions upon millions of collisions produce storms of short-lived particles. Most vanish without surprise. Some leave familiar patterns, and hidden among them are rare decays, delicate little messages from the quantum world, asking whether the rules we know are the rules all the way down. We're not going to rush the answer. We're going to start where the mystery starts, with the beauty meson itself, that brief and unstable particle, whose name sounds almost too graceful for something born in a collision. It is small, heavy, temporary, and wonderfully useful. And once we understand why physicists care so much about how it falls apart, the rest of the puzzle begins to come into focus, one quiet trace at a time. Before the narration, one factual note to keep the story grounded. CERN reported in December 2022 that improved rare B-meson electron and muon measurements agreed with the standard model, superseding earlier hints, while later LHCb updates have continued testing lepton universality in other B meson channels. The beauty meson has a name that sounds far too elegant for the place where it is usually born. You might imagine something delicate, perhaps a small shining thing drifting through a quiet room, but in reality it appears in the aftermath of a collision so energetic that ordinary language becomes a little underdressed for the occasion. Deep underground, inside the Large Hadron Collider, protons are accelerated around a circular tunnel and brought together with astonishing precision. When they meet, they do not simply bounce apart like billiard balls. They break open into energy, and from that energy, new particles briefly come into existence. Some are familiar, some are unstable, some are so short-lived that calling their lives brief almost feels generous. Among them, every now and then, is a B meson. A B meson is not one of the fundamental particles in the deepest sense. It is a composite particle, meaning it is made from smaller ingredients. At its heart is a beauty quark, sometimes also called a bottom quark, along with another quark partner. The name beauty has a certain charm to it, which is slightly confusing because charm is also the name of another kind of quark. Particle physicists, it must be said, have a talent for naming things in ways that sound whimsical, until you're trying to remember them at midnight. Beauty, charm, strange, top, bottom. It can feel less like a scientific classification and more like a very odd guest list for a dinner party. But the beauty quark is not interesting because of its name. It is interesting because it is heavy, unstable, and capable of decaying in ways that make it an excellent probe of the deeper rules of nature. When a B meson is produced, it does not remain a B meson for long. It transforms into other particles, it decays, and in that decay it reveals information, not loudly, not directly, but carefully, statistically, over many thousands and millions of events. A single decay is like one word spoken in a crowded room. Many decays together can become a sentence. Enough sentences can become a message. To understand why physicists became so interested in B mesons, it helps to think about the Standard Model as a set of rules for what particles can do. It does not merely list the particles that exist. It describes how they interact, how they change, how they appear and disappear, and how likely different outcomes are. It is not a book of certainties in the everyday sense. The quantum world is built from probabilities. A particle may have several possible ways to decay, and the theory tells us how often each route should happen if we repeat the process many times. Not every individual event can be predicted exactly, but the pattern should be predictable. This is where B mesons become useful. Many of their decays are complicated. Some are common, others are rare. The rare ones are especially precious because they can be sensitive to hidden influences. If a decay already happens easily through ordinary known processes, then a tiny new effect might be drowned out. But if a decay is naturally suppressed, if the Standard Model allows it only through a more delicate route, then even a small contribution from unknown physics could alter the result in a way that can be measured. Rare decays are like quiet rooms. A whisper becomes easier to hear. The first small crack did not appear as a dramatic announcement that the Standard Model had failed. Science rarely gives us such neat theatre. Instead, it appeared as a tension, a difference between what the theory predicted and what experiments seemed to observe. In certain B meson decays, physicists compared how often the particle produced electrons with how often it produced muons. These two particles are relatives. The electron is light and familiar, part of every atom around you. The muon is heavier, unstable, and mostly known from cosmic rays, particle experiments, and the occasional conversation that begins with, "Actually, there is a heavier cousin of the electron." According to the Standard Model, the weak force should treat electrons and muons almost equally once they're different masses, and the details of the decay are taken into account. This expectation is called lepton universality. The idea is not that electrons and muons are identical in every way. They are not. A muon is much heavier than an electron, and that matters in many processes. But the underlying interaction should not simply prefer one over the other without a reason already included in the theory. If a B meson can decay by producing a pair of muons, and it can also decay by producing a pair of electrons in a closely related way, then the comparison between those rates becomes a clean test of whether nature is playing fairly. For a while, the comparison looked unsettling. Some measurements suggested that decays involving muons might be happening less often than expected when compared with electrons, not by a huge amount, not enough to declare victory over the old theory, but enough to make physicists look twice, then 3 times, then begin writing papers with cautious phrases like intriguing tension and possible deviation. In science, those phrases are the equivalent of someone quietly sitting up in bed because they heard a floorboard creak downstairs. What made the situation more interesting was that it was not only one measurement in isolation. Over several years, different B meson-related results seemed to point toward a similar kind of unease. Some involved rare decays where a beauty quark changed into a strange quark while producing charged leptons. Others involved decays with tau leptons, the heavier member of the lepton family. The details differed, and so did the experimental challenges, but the broad theme was tempting. Perhaps the standard model was not treating all leptons equally after all. Perhaps there was an unknown particle or force affecting some decay routes more than others. Now, this is the point in the story where it is important to lower the volume a little. A crack in physics is not the same as a collapse. When experiments study rare decays, they are working at the edge of what can be measured. The signals are faint. The backgrounds are complicated. Detectors have preferences, not because they are moody, though after years of service one could forgive them, but because different particles interact with the detector in different ways. Electrons are difficult in one way, muons are difficult in another. Comparing them requires an enormous amount of care. An electron, being light and electrically charged, tends to lose energy by radiating photons when it passes through detector material. This can make its energy harder to reconstruct precisely. A muon, heavier and more penetrating, often passes through much more cleanly, leaving a track that reaches the outer muon chambers. This difference is useful, but it also means the detector does not see electrons and muons in identical ways. So if an experiment finds that one type appears more often than another, the first question is not, have we found new physics? The first question is, could the detector have made us think that? This is why particle physics can move slowly even when the headline sounds sudden. A result may take years to prepare. Teams check control channels, compare simulations with data, estimate backgrounds, correct for efficiencies, and test whether the analysis behaves properly on processes where the answer is already known. They blind parts of the data to avoid bias. They argue over uncertainties. They refine methods. They make sure that when they finally look at the sensitive result, they are not simply seeing what they hope to see. It is painstaking work and not especially cinematic unless your idea of cinema is someone staring at a calibration plot while drinking cold coffee. And yet, this patience is exactly why the early B meson tensions became so fascinating. They were not being shouted by people looking for drama. They were being reported by collaborations known for caution. The numbers were not decisive, but they were persistent enough to deserve attention. The standard model had been tested again and again in many places, and here was a region where the match seemed less comfortable. It was as though a beautifully tuned piano had one note that sounded slightly flat. You would not throw away the piano, but you would keep playing that note. The beauty meson itself is an ideal instrument for this kind of test because it sits at a crossroads of particle behavior. It contains a heavy quark, and heavy quarks open doors to many possible decays. Some of those decays involve the weak force, the force responsible for changing one kind of quark into another. The weak force is already strange by everyday standards. It allows particles to transform their identities. It is involved in radioactive decay. It helped shape the early universe. And within B meson decays, it becomes a window into processes that are either very rare or forbidden at the simplest level. Some rare B decays happen only through what physicists call loop processes. Since we're keeping things verbal and gentle, imagine a particle decay that cannot take the direct road. Instead, it must take a detour through a set of temporary quantum possibilities. Along that detour, other particles can briefly participate, not as permanent visible products, but as influences allowed by quantum mechanics. If unknown heavy particles exist, particles too massive to be produced directly with current data or too elusive to stand out clearly, they might still leave fingerprints in these loops. They might slightly change how often a decay happens, or how the outgoing particles are arranged, or whether electrons and muons appear in the proportions the standard model expects. That is the deeper reason the anomaly matters. It is not only about B mesons, it is about whether rare decays can sense things beyond our current reach. The Large Hadron Collider is often imagined as a machine that finds new particles by making them directly, like striking a bell and listening for a new tone. That is one strategy. The Higgs boson was discovered through direct production and decay patterns. But flavor physics, the study of how quarks and leptons change type, often works differently. It can reveal new physics indirectly. It asks whether known particles behave with perfect obedience, or whether something unseen has nudged their probabilities. The first small crack was therefore not a hole in the wall, but a faint line in the plaster. Still, a faint line can matter if it appears in the right place. The standard model predicts lepton universality with great confidence in many contexts. Previous experiments tested it in other systems, and it held up impressively well. So when B meson decays seem to hint that electrons and muons might not be appearing as expected, physicists wondered whether this could be a special doorway. Maybe new physics did not affect all particles equally. Maybe it preferred the heavier generations. Maybe it connected quarks and leptons in a way the standard model does not. Maybe the beauty quark was not just decaying, but revealing a hidden relationship. This possibility drew theorists like moths to a very mathematical lamp. If the anomaly was real, what could explain it? One candidate was a leptoquark, a hypothetical particle that would link quarks and leptons directly. In the standard model, quarks and leptons are separate families. Quarks build protons, neutrons, and mesons. Leptons include electrons, muons, taus, and their neutrinos. A leptoquark would be a bridge between those families. It could allow interactions that alter B meson decay rates in just the kind of way the data seem to suggest. Another possibility was a new neutral force carrier, often called a Z-prime boson, which would act like a heavier cousin of known particles that mediate forces. If such a particle existed, it might influence certain decays without showing itself directly. There were also more elaborate ideas: hidden sectors, new symmetries, connections to dark matter, models where the heavier families of particles have special roles. Some ideas were elegant, some were strained, some were already under pressure from other measurements. In physics, a new idea must survive not just one anomaly, but everything else we know. It is not enough to explain why one window rattles. Your explanation must also account for why the roof has not fallen in, why the door still closes, and why the cat is looking at you as if none of this was surprising. That is one of the great difficulties. The standard model is not easily improved. Many attempts to add new particles create problems elsewhere. A new force that changes B meson decays might also affect other processes that have been measured very precisely. A leptoquark that helps with one anomaly might be constrained by searches at colliders or by rare processes in other particle systems. The universe gives clues, but it also checks the homework. Your theory has to fit into the whole web of evidence, not just the most exciting corner. As more data arrived, the story became more complex. Some of the rare decay measurements that once looked like possible violations of electron and muon universality were later reanalyzed with improved methods and found to agree with the standard model. That was an important development. It showed that at least part of the apparent crack might have been caused by the difficulty of the measurement itself. But it did not erase the entire flavor puzzle. Other tensions remained, especially in comparisons involving tau leptons, and the broader question of whether B mesons are hiding new physics continue to attract serious attention. This may sound like the mystery is becoming less satisfying, but in real science that is often where it becomes more authentic. The universe rarely behaves like a neatly written detective story, where every clue points to the same locked room and the culprit confesses before the final page. More often the evidence shifts. One clue fades, another becomes sharper. A third turns out to be a smudge on the lens. The task is not to defend the most exciting interpretation, but to find the true one, even if it is quieter than expected. The beauty meson teaches this lesson beautifully. It asks us to care about small differences. It asks us to be comfortable with uncertainty. It asks us to understand that a result can be interesting without being conclusive, and that a theory can be extraordinarily successful without being complete. The first small crack may widen, or it may be repaired by better measurements. Either outcome teaches us something. If the anomaly disappears, we learn more about the subtle behavior of detectors, backgrounds, and standard model physics. If it persists and strengthens, then we may be looking at the first clear sign of something beyond the known particle world. There is a quiet humility in that. Physicists do not get to decide which outcome nature chooses. They can only build better instruments, gather more data, and ask sharper questions. The beauty meson decays whether or not we are ready. Its debris flies through the detector. Its tracks are recorded. Its probabilities are counted. Somewhere in those counts, the universe either confirms the old pattern or hints at a new one. And this is why the early anomaly mattered so much. It arrived in a place where the standard model should have been dependable. It involved particles that should have been treated nearly alike. It appeared in processes sensitive to hidden influences. It was small, yes, but not meaningless. A tiny disagreement in the right system can point farther than a loud agreement in an ordinary one. In the world of rare decays, the smallest imbalance can become a lantern. So picture the meson for a moment, not as a diagram or a formula, but as a brief visitor. It appears in the collision, carrying within it the heavy beauty quark. It travels a tiny distance, far too small for human senses, but measurable by a detector built with astonishing care. Then it decays, perhaps into particles involving an electron, perhaps into particles involving a muon, perhaps into a path involving a tau and a neutrino. Each possibility is counted, checked, corrected, and compared. Over time, the counts become ratios, the ratios become tests, and the tests become questions. The first question is simple enough to say, even if it is difficult to answer. Do electrons and muons really behave as the standard model says they should in these decays? The next question is more unsettling. If they do not, what is interfering? And beyond that waits the larger question, the one that gives the whole mystery its shape. Could a short-lived particle born in a collider be pointing toward a deeper layer of nature, one where the known families of matter are connected by rules we have not yet discovered? To reach that point, we need to understand the rule itself, the principle that makes the possible imbalance so important. It is one thing to say that electrons and muons might be appearing at different rates. It is another to understand why that would be so surprising. The standard model does allow particles to differ. It is full of differences. Masses differ, lifetimes differ, interactions differ depending on charge and type. But lepton universality says that beneath some of those differences, the weak force follows a kind of fairness. It couples to the charged leptons in the same basic way. That quiet fairness has been tested again and again, and it is one of the reasons the anomaly drew attention in the first place. The beauty meson, then, is not only the particle in the story, it is the messenger. The first small crack is not merely a strange decay rate, it is a challenge to a principle. And once we understand that principle, once we see why electrons, muons and taus are expected to stand on equal footing in the eyes of the weak force, the mystery becomes sharper, less like a vague disturbance and more like a specific question whispered from the data. To see why the beauty meson measurements caused so much attention, we need to slow down and look at the rule they seem to question. It is called lepton universality. and although the name sounds technical, the basic idea is fairly direct. The standard model says that certain particles known as leptons should be treated in the same basic way by the weak force, not in every detail, because they do not all have the same mass, and mass matters. But once those mass differences are properly included, the weak force should not prefer an electron over a muon, or a muon over a tau, simply because it likes one better. Nature is not supposed to have a favourite lepton. That sentence is simple, but it carries a lot of weight. The electron, the muon, and the tau are three charged leptons. The electron is the one we know best. It is part of every atom around us. It helps make chemistry possible. It is in the wall beside you, the blanket near you, the screen glowing in the room, and the muscles moving your hand if you are adjusting your pillow right now. It is light, stable, and deeply familiar, even if most of us do not spend breakfast thinking about it. The electron is one of the reasons matter has structure. Without electrons, atoms would not behave as atoms, molecules would not form in the usual way, and tea would have a very difficult time being tea. The muon is similar to the electron in many respects, but it is heavier and unstable. It has the same kind of electric charge as the electron, and it belongs to the same lepton family, but it does not stick around. Muons are produced naturally when cosmic rays strike the upper atmosphere, sending showers of particles down toward Earth. Some pass through your body every minute without asking permission, which is rather rude, but harmless in the ordinary course of life. Muons are also produced in particle accelerators, where physicists use them as useful messengers because they can travel through detector material in a clean and recognizable way. A muon is like an electron that has put on a heavy coat, walked through a wall, and then disappeared before anyone could ask where it was going. The tau is heavier still, and even more short-lived. It is the third charged lepton, the largest of the three, and it decays very quickly into lighter particles. Because it is heavy, it can behave in ways that make it harder to study but also especially interesting. If new physics were hiding in the way particles of different generations interact, the tau might be a place where the effect becomes more noticeable. In that sense, the tau is inconvenient in exactly the way that makes it valuable. It does not make the experiment easy, but it may make the question sharper. Each of these charged leptons also has a neutrino partner. There is an electron neutrino, a muon neutrino, and a tau neutrino. Neutrinos are extremely light and interact so weakly with matter that vast numbers of them pass through Earth all the time. They are not the main focus of the B meson anomaly in the simplest telling, but they complete the family picture. Leptons come in generations, and the electron, muon, and tau represent three versions of a similar idea, increasing in mass as we move from one to the next. Why nature has three generations at all is one of those questions that sounds basic, and becomes deeper the longer you stare at it. Lepton universality says that the weak force couples to these charged leptons in a universal way. The weak force is one of the fundamental interactions in the standard model. It is responsible for processes where particles change identity. It allows certain forms of radioactive decay. It plays a role in how stars shine and how particles transformed in the early universe. Unlike electromagnetism, which is familiar through light, magnets, electric currents, and the small shock you get from a sweater on a dry day, the weak force works over extremely short distances. It is not something we feel directly. It does not push your chair across the floor. It does not hold a fridge magnet in place. But inside the particle world, it is essential. When the weak force acts, it should see the electron, muon, and tau as members of the same category. Again, this does not mean their outcomes always look identical. If a decay does not have enough energy to make a tau, then the tau will not appear. A heavy particle is harder to produce than a light one in many situations. A tau also decays quickly, which complicates detection. So the rule is not a childish kind of equality, where every event must produce the same thing in the same amount. It is a more careful statement. The underlying weak interaction should be the same for the three charged leptons, after the practical consequences of their different masses have been included. A useful way to think about it is to imagine a fair doorway. The doorway itself is not biased. It does not prefer one person over another. But if 3 people approach it carrying different sized boxes, their passage through the doorway may look different. One passes easily. One slows down slightly. One has to turn sideways and shuffle through with a great deal of effort. The doorway has not changed its rules. The difference comes from what each person is carrying. In particle physics, the different masses of the leptons are like those different boxes. The weak force should provide the same doorway, while the mass differences explain why the details of the passage can vary. This is why ratios are so important in B-meson studies. Physicists often compare related decay processes involving different leptons. They ask whether a B-meson decay that produces muons happens at the expected rate, compared with a similar decay that produces electrons. By making comparisons, many experimental difficulties can partly cancel. It is still difficult because electrons and muons leave different signatures in detectors, but the comparison is cleaner than simply measuring an isolated decay rate and trying to interpret it alone. A ratio can become a powerful test of fairness. For many years, lepton universality has been tested in different settings, and the standard model has done very well. That is why the B-meson hints were taken seriously. They did not appear in a part of physics where no one knew what to expect. They appeared in a region where a strong rule already existed. When a well-tested rule seems to bend, even slightly, physicists pay attention. Not because they want the rule to fail, but because the most valuable clues often appear where the theory makes a clear prediction. The standard model is not a loose collection of guesses. It is a tightly connected structure. If you change one part of it, other parts feel the change. This is one reason new physics is so difficult to find. You cannot simply say that muons should behave differently in B-meson decays without asking what else that change would affect. Would it alter other rare decays? Would it change how particles are produced at colliders? Would it create signals in older experiments that should already have been seen? Would it conflict with precision measurements made over decades? A good explanation has to survive the whole network. Lepton universality has a special place in this network because it is both simple to state and difficult to test perfectly. The electron, muon and tau are not equally easy to measure. Electrons interact strongly with detector material through electromagnetic processes, and they can radiate energy that must be recovered or corrected for. Muons tend to pass through more material and are often identified with high reliability. Taus decay almost immediately into other particles, sometimes including neutrinos that escape undetected. This means an apparent difference between leptons can come from the detector, from the reconstruction, from backgrounds, or from the physical decay itself. Untangling those possibilities is the heart of the work. Imagine trying to compare how often 3 kinds of birds visit a garden, but one is large and easy to see, one is small and darts behind leaves, and one only comes out at dusk while carrying a blanket over its head. If your count shows fewer of the third bird, you cannot immediately conclude that nature dislikes it. You must ask whether your method is missing it. Particle detectors are much more precise than garden watching, of course, and usually involve fewer blankets, but the logic is similar. Before claiming a fundamental difference, the experiment must understand how each particle type is being seen. This is why the anomalies did not instantly become discoveries. A difference in the data is only the beginning. Physicists must estimate how likely it is that the difference came from ordinary statistical variation. They must study whether the detector responded differently to electrons and muons in a way that was not fully accounted for. They must test the same methods on other decays where lepton universality is expected and already well established. They must compare results across years, across analysis methods, and eventually across experiments. It is slow because it has to be slow. A careless announcement would not reveal new physics, it would only reveal impatience. Still, the reason the B-meson situation became so exciting is that lepton universality is not just a minor bookkeeping rule. If it were truly violated in these decays, it would point directly beyond the Standard Model. The Standard Model contains lepton universality in its weak interactions. A confirmed violation would mean that something else is contributing. That something might be a new particle, a new force, or a deeper structure that changes how the generations of matter relate to one another. It would not merely be a correction in a table. It would be evidence that our current theory is incomplete in a measurable way. One proposed possibility involves leptoquarks. These hypothetical particles would connect quarks and leptons directly. In the Standard Model, quarks and leptons are different classes of matter. Quarks make up particles such as protons, neutrons, and mesons. Leptons include electrons, muons, taus, and neutrinos. They interact through known forces, but there is no ordinary Standard Model particle whose job is to turn a quark and a lepton into a directly linked pair in the way leptoquark theories suggest. If leptoquarks exist, they could influence B-meson decays and potentially treat different leptons differently. That makes them natural suspects in a story about beauty quarks and uneven lepton outcomes. Another possible explanation involves a new force-carrying particle often called a Z-prime boson. The familiar Standard Model already includes neutral particles that mediate weak interactions. A Z-prime would be an additional heavy neutral particle associated with a force not yet observed directly. If such a particle interacted more strongly with muons than electrons, or with particular combinations of quarks and leptons, it could shift the probabilities of rare B-meson decays. It might not appear directly as a clear new bump in collision data if it is too heavy or too weakly coupled, but it could still leave an indirect trace. There are also broader possibilities. Perhaps the three generations of matter are not merely copies with different masses. Perhaps they have a hidden pattern. The electron, muon, and tau may look like variations on a theme, but no one knows why the theme repeats 3 times. The quarks also come in 3 generations. The first generation makes ordinary matter. The second and third appear mainly in high-energy processes and unstable particles. The Standard Model describes these generations, but it does not explain why they exist in this particular arrangement. A violation of lepton universality could be a clue that the generations are connected by a deeper rule. This is one of the reasons flavor physics is so important. Flavor is the name physicists give to the different types of quarks and leptons. It is an odd word, but it captures the idea that particles come in several varieties. Studying flavor means studying how these varieties behave and transform. Many of the biggest questions in particle physics are flavor questions. Why are there 3 generations? Why do their masses differ so drastically? Why do quarks mix with one another in one pattern, while neutrinos mix in a very different pattern? Why is matter more abundant than antimatter in the universe? These are not side issues, they are central clues. B-meson decays sit right in this territory. A beauty quark can transform into other quarks through weak processes. These transformations are governed by patterns that the Standard Model describes, but does not fully explain at a deeper level. When leptons appear in the final products, physicists can test whether the lepton side of the process behaves as expected. If the lepton pattern looks uneven, the result may be pointing to a connection between quark flavor and lepton flavor that the Standard Model does not contain. The word universality might make the rule sound absolute and simple, but in practice it is a carefully tested expectation. In some decays, mass differences matter a lot. In others, they matter very little. Electrons are so light compared with many particle masses that they often behave almost as if their mass can be ignored. Muons are heavier, but still light compared with B mesons. Taus, however, are heavy enough to make a major difference. So tests involving taus are especially sensitive to how well the theory handles mass effects, and to whether new physics might prefer heavier leptons. This is part of why B decays involving taus remain so interesting. They are harder to measure, but they may be more exposed to certain kinds of new interactions. There is another subtle point. If a new force or particle exists, it does not have to treat all leptons equally. In fact, many proposed theories are designed precisely because they do not. They may couple more strongly to muons than electrons, or to taus more than muons, or to the second and third generations more than the first. That might sound arbitrary, but it could reflect a hidden structure. The masses of the leptons already differ dramatically, so perhaps those differences are not accidental. Perhaps they are signs of a deeper organization we do not yet understand. Lepton universality would then be an excellent approximate rule at low energies, or in many ordinary processes, but not the final truth. This is how science often advances. A rule works extremely well, until a more precise measurement shows where it is limited. Newtonian gravity worked beautifully for everyday motion and planetary orbits, but small discrepancies in Mercury's orbit eventually became one clue pointing toward general relativity. The old theory was not useless. It was a very good approximation in a wide range of situations. In the same way, the standard model may remain an extraordinary description of known particles while still being incomplete. If lepton universality were violated in a real and reproducible way, it would not mean the standard model was foolish. It would mean it was part of a larger story. But the word if must stay with us, if the anomaly is real, if the measurements continue to hold, if independent analyses confirm the same pattern. If the theoretical predictions are under control, that small word is the difference between curiosity and discovery. The B-meson results have moved over time. Some earlier hints have weakened. Some comparisons now agree with the standard model more closely than they once appeared to. Other tensions remain under investigation. This shifting landscape is not a failure. It is the process of measurement becoming sharper. The fog thins, and sometimes the shape inside it turns out to be a tree rather than a door. For a listener drifting towards sleep, there is something useful in that patience. The universe does not owe us immediate answers. It allows us partial views, imperfect hints, and questions that take years to phrase correctly. Lepton universality is one of those questions phrased in a clean way. Do the charged leptons receive equal treatment from the weak force? In many cases, the answer appears to be yes. In certain B-meson studies, the answer has been tested with increasing precision, because there have been hints that the answer might not be entirely simple. That is enough to keep the field attentive. The experiments themselves are remarkable acts of comparison. They are not merely counting particles. They are comparing what is seen with what should have been seen, correcting for how the detector behaves, and translating brief electronic signals into statements about fundamental interactions. Every electron candidate, every muon track, every reconstructed decay has to pass through layers of selection and analysis. Background processes must be estimated and removed. Simulated events must be checked against real data. Control samples must show that the machinery is reliable. Only then can a comparison become meaningful, and all of this is done because the rule is so important. If electrons and muons are treated alike, the standard model survives another test. If they are not, then something beyond it must be contributing. There is very little middle ground. A confirmed violation would be a clean sign that the known forces are not the whole story. It would suggest that the lepton family has hidden structure, or that quarks and leptons communicate through an unknown channel, or that a new force is present but subtle. It would give physicists not just a mystery but a direction. That is why the phrase lepton universality appears again and again in discussions of the B-meson anomalies. It is the quiet rule behind the noise. It is the reason a small difference in decay rates can matter. Without that rule, the anomaly would be just another measurement. With it, the anomaly becomes a test of whether nature follows one of the standard model's most elegant assumptions. The beauty meson is the messenger, but lepton universality is the message being tested. So when we say that B-mesons may not be behaving as expected, we are really saying something more specific. We are asking whether the weak force treats the electron and the muon equally in these rare decays. We are asking whether the tau is following the pattern predicted for it after its heavy mass is included. We're asking whether the three charged leptons are truly variations of the same weak interaction theme, or whether one of them is hearing a faint extra note from somewhere outside the standard model. It is a careful question, but a profound one. The electron is part of every atom in ordinary matter. The muon arrives from cosmic rays and particle collisions, heavier and temporary. The tau is heavier still, flickering briefly before it decays. These three particles are connected but not understood as deeply as one might expect. The standard model tells us how they behave, but not why the family exists in exactly this form. If meson decays show that the weak force distinguishes among them in an unexpected way, then we may be seeing the edge of a deeper explanation. For now, the rule remains standing, but it is being tested with unusual care. The data have not delivered a final verdict. They have given physicists a reason to keep looking, and in the underground detectors at CERN, that looking continues through the quiet accumulation of events. A B-meson forms, travels a tiny distance, and decays. An electron appears in one case, a muon in another, a tau perhaps in a harder, messier channel. Each event is small, each one alone says almost nothing. But together, they ask whether fairness is truly built into the weak force, or whether the universe has been keeping a preference so subtle that only the rarest decays could reveal it. That question leads naturally into the next part of the puzzle, because the rule itself is only half the story. The other half is what the experiments actually saw. Not as a headline, not as a dramatic declaration, but as a pattern in the data, where electrons and muons seemed for a while to be arriving in proportions that made physicists lean closer to the screen and check the numbers again. For grounding, I'm treating the electron and muon rare decay story carefully, because official CERN and LHCb updates have shown that some earlier lepton universality tensions moved closer to the standard model, while other B decay tensions and newer tests remain important parts of the wider puzzle. The odd thing about an uneven whisper is that, at first, it does not sound like much. It is not a shout from nature. It is not a crack of thunder rolling through the underground tunnel. It is not the detector lighting up and politely announcing that the universe has made a mistake. It is a slight difference, a small imbalance, a pattern that appears only after many events have been gathered, filtered, corrected, compared, questioned, doubted, and then compared again. If you were standing beside the experiment itself, you would not feel it. You would not hear anything unusual. The protons would continue their circular race. The collisions would continue. The computers would continue sorting signals from noise. And somewhere inside an ocean of ordinary outcomes, electrons and muons would begin to seem as though they were not quite arriving in the proportions the standard model had led everyone to expect. This is where the story becomes both delicate and difficult. Electrons and muons are not exotic strangers to particle physics. The electron is deeply familiar, woven into ordinary matter, chemistry, electricity, and the everyday stability of atoms. It is so common that it can seem almost humble. It is in the lamp beside the bed, the wood of the nightstand, the glass of water, the page of a book, and the skin of the hand turning that page. The muon, by contrast, is heavier and short-lived. It does not build ordinary atoms in the usual quiet way. It appears when cosmic rays strike the atmosphere, and it appears in the debris of high-energy particle collisions. It passes through matter with a certain calm persistence, often leaving clean tracks in detectors before it decays. If the electron is the reliable resident of the material world, the muon is the visiting cousin who arrives from the upper atmosphere or the collider tunnel, leaves a signature, and vanishes before dinner. Yet, in the eyes of the weak force, these two particles should be treated almost the same. That is the essential point. The electron and the muon have different masses, and those masses matter in some situations. But in certain rare B-meson decays, once physicists account for the known differences, the standard model predicts that the rates involving electrons and muons should match in a particular way. The comparison is not based on a vague feeling that things ought to be equal. It is a precise expectation built into the structure of the theory. The weak interaction does not know the electron as a beloved local citizen and the muon as an interesting visitor. It should couple to them with the same basic strength. So when early measurements suggested that B mesons might be producing muons less often than expected compared with electrons, the result landed in the scientific community with a quiet force. Not as proof, not as certainty, but as an invitation to look harder. The phrase less often than expected can sound simple, but it hides a large amount of work. A B meson is produced in a collision, travels a tiny distance, and decays. The detector does not see the B meson in the way the eye sees a bird crossing the sky. It reconstructs the event from traces. Charged particles leave tracks. Some particles deposit energy in calorimeters. Muons pass through layers and reach outer chambers designed to identify them. Electrons behave differently, losing energy in ways that must be carefully recovered. The experiment records all of this, and then the analysis begins. The raw event is not yet a conclusion. It is only the beginning of a careful reconstruction. Imagine trying to understand a brief scene in a dark room after everyone has already left. You did not witness the conversation directly. You find footprints, a moved chair, a warm cup, a coat left on the back of a seat, a door not quite closed. From these clues, you infer who was there and what may have happened. Particle physics does something similar, though with far more precision and rather less furniture. A decay is reconstructed from what remains. The outgoing particles become clues to the short-lived parent that produced them. Now in many B meson decays, the standard model expects certain electron and muon outcomes to appear at nearly matching rates when compared in the right way. This is useful because comparing them can cancel some sources of uncertainty. If you were measuring only one decay rate by itself, many difficulties would remain. How many B mesons were produced? How efficiently were they reconstructed? How many background events imitated the signal? But when two very similar decay pathways are compared, some common uncertainties shrink. This makes the electron versus muon comparison a particularly clean test of lepton universality. Clean, however, does not mean easy. Electrons and muons are not equally cooperative in a detector. Muons are often easier to identify because they travel through material and reach dedicated muon detectors. They leave long, recognizable tracks, almost like someone walking through fresh snow in a straight line. Electrons are more delicate. As they pass through detector material, they can radiate light particles and spread their energy in ways that make the reconstruction more complicated. They are like guests who enter the room wearing glitter and somehow leave evidence on everything. Very useful, very real, but requiring patience to account for properly. This difference matters because any apparent imbalance between electrons and muons could come from the detector rather than from nature. If electrons are harder to reconstruct, then a careless analysis might undercount them. If muons are easier to identify, a comparison could be biased in the other direction. If background processes imitate one channel more than another, the result could shift. This is why the experiments do not simply count and announce. They calibrate, they test, they compare with known processes. They use control samples, which are decays that should behave in well-understood ways, to make sure the detector response is being described correctly. They ask whether the measuring instrument itself is whispering before they decide the whisper came from the universe. The first hints were intriguing because, after all that care, some numbers still seemed low on the muon side. In certain rare decays, B mesons appeared to produce muon pairs less frequently than the standard model prediction suggested when compared with electron pairs. The effect was not enormous. It was not a result so overwhelming that all doubt vanished. Particle physicists measure surprise in a disciplined way, and these early tensions were not high enough to claim discovery. But they were high enough to make people take notice, especially because similar themes appeared in more than one place. This is important. One odd measurement can happen for many reasons. A statistical fluctuation can rise and fall like a bubble in water. A small imperfection in an analysis can create an apparent excess or deficit. A background estimate can shift. But when several measurements begin to point in a related direction, physicists become more interested. Not convinced, but interested. The meson data did not simply say, "Here is one strange count." It suggested in several corners that perhaps muons or heavier leptons were not behaving quite as expected. The pattern was subtle, but patterns are what science is trained to notice. The rare decays involving electrons and muons became especially famous because they tested lepton universality in a clear way. A beauty quark inside a B meson can transform into a strange quark while producing a pair of charged leptons. In the standard model, this kind of process is rare. It does not happen through the simplest direct weak interaction path. It occurs through more complicated quantum routes, the sort of routes where new heavy particles, if they exist, might quietly influence the outcome. That is why these decays are valuable. They are not ordinary roads. They are narrow paths through the forest, and if something unknown has stepped there, its footprints may remain visible. When the muon channel looked suppressed, one possible interpretation was that a new particle or interaction was interfering with the decay. Perhaps there was a new force that coupled more strongly to muons than to electrons. Perhaps a leptoquark was linking quarks and leptons in a way the standard model does not allow. Perhaps a heavier neutral force carrier was altering the probability of one pathway. These ideas were not declarations. They were attempts to explain what the data would mean if the pattern were real. Theorists began building models that could shift the muon rate without ruining everything else the standard model already explains. That last part is always the challenge. A new explanation must not only solve the puzzle on the table, it must avoid knocking over every other piece of furniture in the house. The uneven whisper also appeared alongside another kind of unease in B physics. Some rare B meson decay rates, especially in channels involving muons, have been measured lower than theoretical expectations. This is related to, but not identical with, lepton universality. A lepton universality test asks whether electrons and muons appear in the expected relative amounts. A branching fraction measurement asks how often a particular decay happens at all. If a muon decay happens less often than predicted, that may be interesting. If it happens less often than the electron version in a way the standard model does not expect, that becomes a sharper test of universality. These are different questions, but they can point towards similar possibilities if the pattern holds. For a while, the picture looked as though it might be assembling itself. Rare decays involving muons seemed low. Ratios comparing muons and electrons seemed low. Measurements involving tau leptons showed their own tensions. It was not one perfectly clean arrow, but it was enough to make people wonder whether the standard model was missing a piece connected to lepton flavor. Flavor is the word physicists use for the different types of particles within families, and in this context it means the distinction between electrons, muons and taus, as well as the different quarks. The word sounds almost culinary, as if the universe is running a very serious ice cream counter, but the physics is deep. Why do these families exist? Why 3 generations? Why these masses? Why these patterns of transformation? Flavor has always carried unanswered questions. Still, the universe is allowed to be less dramatic than our theories. As more data were analysed, some of the electron and muon tensions changed. Improved LHCb studies using larger datasets and refined methods found that certain earlier rare decay ratios were consistent with the standard model. The whisper, at least in those channels, became softer. Some headlines had once treated the anomaly as though new physics were already peeking through the doorway. Later results reminded everyone that the doorway might have been a shadow. This is not a failure of science. It is science breathing properly. A surprising result is tested. If it fades, the knowledge improves. If it remains, the case strengthens. Either way, nature wins. But the story did not become empty. Other anomalies in B physics have persisted in various forms, and tests involving tau leptons continue to be important. The tau is heavier, harder to reconstruct, and often produces neutrinos that escape the detector unseen. That makes tau measurements more difficult than electron or muon measurements, but also potentially more sensitive to certain new physics ideas. Some models that were proposed to explain the electron and muon anomalies also have consequences for tau decays. So even as certain rare electron and muon ratios moved closer to standard model expectations, the wider field did not pack up and go home. It adjusted. It became more precise. It asked better questions. That is the rhythm of modern particle physics. A hint appears, theorists explore what it could mean, experimentalists gather more data and refine the analysis. Some possibilities are ruled out, others survive. The excitement narrows, but it also sharpens. It is a little like walking through a house at night with a flashlight. At first, every shape in the corner could be something mysterious. Then the beam moves, and most of them become coats, chairs, and ordinary shadows. But if one shape remains strange after the light reaches it, then you have a reason to step closer. The electron and muon comparison is especially valuable because it is one of the cleanest ways to ask whether new physics distinguishes between lepton generations. If a hidden force exists and it treats muons differently from electrons, it may show up in these rare decays. If a leptoquark connects beauty quarks with muons more strongly than with electrons, it may shift the rates. If the standard model is complete in this region, the ratio should settle where predicted as measurements improve. The test is simple in concept, even though the execution is immensely difficult. Count the right decays. Correct for the detector. Compare the lepton outcomes. Ask whether nature is fair. Of course, fairness in physics is not moral fairness. The universe is not making ethical decisions about electrons and muons. It is following interaction rules. Lepton universality is a symmetry of behavior, a statement about how the weak force couples to different charged leptons. If that symmetry is broken, it would mean there is structure underneath the known rule. It would be like discovering that two doors in a hallway, painted the same colour and measured to the same width, actually lead to different buildings. The difference may not be visible from the outside, but it changes the architecture. One reason the anomalies captured public imagination is that they seem to offer a concrete path beyond the standard model. Everyone in particle physics knows the standard model is incomplete. It does not explain dark matter. It does not include gravity as a quantum force. It does not explain the full pattern of particle masses. It does not answer why matter dominated over antimatter in the early universe. But knowing a theory is incomplete is not the same as knowing where it breaks. A general sense of incompleteness is like knowing there must be a hidden room somewhere in a mansion. An anomaly is hearing a draft under one particular wall. The meson data suggested that the wall might be in flavor physics, not necessarily at the highest energy frontier where new particles appear directly, but in the subtle probabilities of known particles decaying. This is an old and powerful strategy. New physics can appear indirectly before it is seen directly. In the past, studying rare processes and precision measurements helped reveal the existence or properties of particles before they were produced in experiments. The quantum world allows unseen particles to affect measurable outcomes, so long as the effects are small enough and consistent with known rules. A rare decay can therefore become a telescope aimed not outward into space, but inward into possibility. The challenge is that rare decays are rare for a reason. The experiment must sift through enormous numbers of events to find the few that matter. Backgrounds can imitate the signal. Some particles are misidentified, some decay products escape. The detector response changes with energy, position, and time. The analysis must account for all of this. A small imbalance is meaningful only if every ordinary explanation has been chased down with patience. The less dramatic the anomaly, the more careful the work must be. A huge effect can announce itself. A small one must be protected from wishful thinking. This is why the phrase "nobody can explain" should be handled gently. It does not mean nobody has proposed explanations. Many people have. It means no explanation has yet been confirmed as the true one. It may be new physics. It may be an underestimated standard model effect. It may be a subtle experimental issue. It may be a statistical fluctuation that fades with more data. In science, unexplained does not mean magical. It means the evidence has not yet settled into a single clear interpretation. That uncertainty is not a weakness. It is the honest shape of the frontier. There is another layer here, because the standard model predictions themselves can be difficult in some B-meson decays. When quarks are bound inside mesons, the strong force complicates the calculation. Quarks are never simply sitting alone like marbles on a table. They are confined inside particles, surrounded by gluons and quark activity. This makes some predictions challenging, especially for absolute decay rates. Ratios comparing electrons and muons can be cleaner, because many strong force uncertainties cancel, but not every observable is equally simple, so the uneven whisper in the data must be compared not only with detector performance, but also with theory predictions and their uncertainties. Both sides of the comparison need care. This is one reason physicists like multiple observables. They do not want to rely on a single number. They study decay rates, angular distributions, ratios between lepton types, related decays involving different mesons, and channels with different final particles. Each observable has its own strengths and weaknesses. If new physics is present, it should leave a pattern across several of them. If an anomaly appears in one place but nowhere else, it may be a local issue. If several independent measurements tell a related story, confidence grows. The goal is not simply to find a surprising number. The goal is to find a coherent picture. For the listener, it may help to imagine tuning an old radio. Most of the dial is static. Then, faintly, a voice appears. You turn the knob a little. The voice fades. You turn back. It returns. You adjust the antenna. Maybe it is a station. Maybe it is interference. Maybe it is a passing truck outside affecting the signal. The only way to know is to keep tuning, check other frequencies and see whether the message becomes clearer. B-meson anomalies have been like that. There has been a voice in the static, but it has not yet spoken clearly enough to write down the message with confidence. Electrons and muons, then, are more than particles in this story. They are comparison tools. They are two nearly matched probes sent through the same rare decay machinery. If they emerge in the predicted balance, the standard model gains another quiet victory. If they do not, then something new may be shaping the process. The beauty of the test lies in its restraint. It does not ask for a spectacular new object to burst into view. It asks whether two familiar particles are being treated equally in a rare transformation. A very small question, on the surface, a very large one underneath. And perhaps that is why the uneven whisper stayed in the imagination even as parts of it softened. The idea that electrons and muons might not be treated equally touches something fundamental. It suggests that the families of matter may have hidden differences beyond mass. It hints that the second generation, the muon generation, may be connected to new forces or particles in a way the first generation is not. It raises the possibility that ordinary matter, made mostly from first-generation particles, is only the most visible layer of a deeper family structure. The particles that seem temporary and exotic to us may hold the clues to why the universe has the shape it does. At CERN, the work continues because the question is too important to leave half-answered. LHCb has been upgraded to collect more data and handle more collisions. New measurements will test lepton universality with greater precision. Other experiments also contribute, comparing their own results and searching for related signs. The data from future runs may show that the remaining anomalies fade into agreement. Or they may show that one of the whispers grows clearer. Both outcomes matter. A disappearing anomaly teaches physicists how subtle the known world can be. A surviving anomaly may point to something genuinely unknown. For now, the electron and muon story is a lesson in scientific caution. It shows how a small discrepancy can ignite enormous interest, but also how carefully that interest must be handled. The public version of the story may want a clean sentence. CERN found something impossible. Physics is broken. A new force has arrived. The real version is quieter. Certain B-meson decays showed tensions with standard model expectations. Some tests of electron and muon universality once appeared lower than predicted. Later analyses brought some of those tests closer to agreement. Other B-decay puzzles remain under study. The answer is not yet final. That may sound less exciting, but it is more truthful, and in a way more beautiful. We are watching knowledge form in real time. Not the polished version that appears in textbooks, where every idea seems to lead smoothly to the next, but the living version, where uncertainty breathes, retreats, returns, and changes shape. Electrons and muons are being counted not because anyone expects them to be dramatic, but because if they are even slightly unfairly treated, the consequences could reach far beyond the decay itself. The uneven whisper in the data is therefore not one single sound. It is a collection of small questions. Why did some rare muon channels appear suppressed? Why did some lepton universality ratios once sit below expectation? Why do some tau-related measurements still draw attention? Why do certain patterns in flavor physics seem to invite explanations beyond the standard model, even when individual anomalies shift with better data? These questions do not yet form a discovery, but they form a map of where to look. And the map leads back to the detector, to the place where the whisper is gathered event by event. To understand how such small imbalances can be seen at all, we need to move closer to LHCb itself, not just as a name attached to a result, but as a machine built for this kind of listening. A detector designed to catch the brief signatures of beauty particles, to distinguish electrons from muons, to reconstruct decays that happen almost as soon as the particles are born, and to turn the debris of collisions into a careful question about the deepest rules of matter. CERN describes LHCb as a 5,600-ton experiment built to study particles containing beauty quarks, with movable tracking detectors placed close to the beam path so these short-lived particles can be reconstructed from their decay products. The experiment is designed to study beauty and charm particles created in Large Hadron Collider collisions, even though the quarks themselves are never observed directly and must be understood through the unstable particles they form and the particles those states decay into. To understand how a tiny imbalance between electrons and muons can become a serious scientific question, it helps to step inside the experiment that hears it. Not literally, of course. One does not simply wander into a particle detector as if entering a library, especially not while protons are being circulated around the Large Hadron Collider. But we can imagine ourselves standing near the place where the machine rests underground, close to the border between Switzerland and France, where the countryside above looks ordinary enough. Roads, fields, buildings, a horizon that gives no obvious sign that below it, some of the fastest and most carefully controlled particles on Earth are being guided through a circular tunnel. It is one of the strange comforts of modern physics that the deepest questions about matter can be asked beneath a landscape where someone might also be walking a dog. The Large Hadron Collider beauty experiment, usually called LHCb, is not the largest looking of the great collider detectors in the way people often imagine. It is not shaped like a vast barrel wrapped around the collision point in all directions. It has a more specialized shape, and that shape comes from the behavior of the particles it wants to catch. When protons collide at high energy, beauty quarks and their antimatter partners are often produced in a forward direction, meaning they tend to fly closer to the path of the original beams, rather than spreading evenly in every direction. LHCb was built to take advantage of that. It is arranged like a long, highly instrumented listening corridor, watching the region where many of these beauty particles are most likely to travel. That shape already tells us something important. This is an experiment built not merely to see that something energetic happened, but to follow what happened next. A beauty meson appears in the collision and almost immediately decays. It may travel only a tiny distance before transforming into other particles, but that tiny distance matters. It gives the detector a clue. If a particle is born at the collision point and then decays a little way away, its decay products may seem to emerge from a secondary point, not exactly where the proton collision occurred. Detecting that displacement is one of the keys to recognizing beauty particles. In everyday terms, it is like noticing that footprints do not begin at the front door, but a few steps inside the room. Something entered unseen and then left traces. The part of LHCb that makes this possible is the vertex locator. The word vertex in this context means a point where particles originate or decay. The vertex locator sits extremely close to the beamline, close enough that it must be engineered with extraordinary care. It tracks charged particles soon after the collision and helps reconstruct the exact points where they came from. For B-meson physics, this is essential. These mesons live so briefly that only a detector with very fine spatial precision can separate their birth from their decay. Without that ability, many of the rare processes we have been discussing would blur into the general debris of the collision. The vertex locator is a little like the experiment's memory of place. It remembers where the collision happened, and it helps identify where something else happened a fraction of a moment later. From that difference, physicists can infer that a short-lived particle travelled between the two. It is an almost absurdly delicate task. The distances are tiny by human standards, and the events happen far faster than any human sense can register. Yet the detector records them again and again, with patient electronic attention, building a map from particles too small to see and times too short to imagine comfortably. After the vertex locator, the next task is to follow the charged particles as they move through the detector. Tracking systems measure their paths. A magnet bends those paths. The amount and direction of the bending reveal information about the particle's momenta and charges. This is one of the oldest ideas in particle detection, refined into a modern form of extraordinary precision. Charged particles moving through a magnetic field curve, and the curvature becomes a clue to their identity and motion. In the detector, tracks are not simply lines, they are evidence. They tell physicists how the debris of the decay moved, which particles may have been involved, and whether the reconstructed story is consistent with a B-meson decay. This tracking is especially important because B-meson decays do not arrive neatly labelled. The detector does not receive a message saying, "Here is a rare decay involving a beauty meson, please handle carefully." It receives many tracks, many deposits of energy, many signals from different systems, all overlapping with the remnants of the collision and with other activity in the event. The experiment must reconstruct the likely chain of events. A beauty meson may have decayed into a strange meson and two charged leptons, or into a different combination of particles, or the apparent signal may be partly background, an ordinary process wearing the costume of something rare. The tracking system helps sort those possibilities. Then comes one of the detector's most distinctive abilities, particle identification. It is not enough to know that a charged particle passed through. LHCb needs to know what kind of charged particle it probably was. Was it a pion, a kaon, a proton, an electron, a muon? These distinctions are crucial because the decay being studied may depend on identifying exactly which particles appeared at the end. In B-meson physics, misidentifying one particle as another can turn an ordinary event into an apparent rare one, or hide a rare event among ordinary backgrounds. The detector must therefore be not just sensitive but discriminating. One of the major tools for this is the ring-imaging Cherenkov system. The name sounds grand, and in fairness, it is. Charged particles passing through certain materials can produce a faint cone of light if they move faster than light travels through that material. This does not mean they move faster than light in empty space, so no need to alert Einstein at this hour. It simply means light slows down inside a medium, and a particle can outrun light in that medium, producing a characteristic glow. By measuring the pattern of that light, the detector can help identify what type of particle passed through. CERN has described continuing upgrades to the ring-imaging Cherenkov system, including electronics designed for high-rate data collection and precise timing of the detected light. This is one of those places where the detector begins to feel less like a single machine and more like a set of sensors. The vertex locator senses where particles began and where they decayed. The tracking system senses how charged particles moved. The Cherenkov detectors help sense what kinds of particles they were. Calorimeters measure energy, especially for particles such as electrons and photons that deposit their energy in showers. Muon chambers identify muons, those heavier cousins of electrons that can travel through layers of material and still leave clear signals in the outer parts of the detector. Each system sees part of the story. None sees everything alone. The full event is reconstructed by combining their reports. Electrons and muons, the central pair in the lepton universality tests, are especially different from the detector's point of view. A muon behaves almost like a calm traveller passing through the station. It leaves a track in the inner detector, continues through the calorimeters with relatively little fuss, and reaches the muon system, where dedicated chambers confirm its presence. This makes muons comparatively clean to identify. They are not effortless, because nothing in a collider detector is effortless, but they are cooperative in a way that physicists deeply appreciate. Electrons are more restless. They interact electromagnetically with detector material and can radiate energy as they pass through. They create showers in the electromagnetic calorimeter. Their energy can be spread out or partially carried away by emitted light particles, and the analysis must recover and correct for this behavior. If the goal is to compare electron and muon decay channels, this difference is not a minor technical footnote. It is one of the central experimental challenges. The detector is not equally transparent to both particles. Nature may treat them universally, but the apparatus does not experience them in the same way. That is why LHCb's measurements are so careful. A simple count would not do. Suppose the experiment sees fewer electron events than muon events, or fewer muon events than electron events. Before asking whether the weak force has broken its rule, physicists must ask whether the detector has simply responded differently. Were some electrons missed? Were some muons misidentified? Did background processes contaminate one channel more than another? Did the trigger system select one kind of event more efficiently? Did the simulation correctly describe the detector material? Did the calibration remain stable over time? These questions are not distractions from the discovery. They are the road to knowing whether there is a discovery at all. The word trigger deserves a quiet moment of its own. The Large Hadron Collider produces far more collision events than can be stored in full detail. A detector cannot keep everything. It must decide very quickly which events are worth saving for deeper analysis. In older collider experiments, this often involved layers of hardware and software decisions that filtered the data in real time. LHCb has undergone major upgrades to improve the way it reads out and selects events, allowing more flexible and detailed choices in software. This matters enormously for rare decay searches. When the thing you seek happens only rarely, the ability to keep the right events can determine whether the whisper is heard at all. Think of trying to listen for one quiet sentence spoken in a crowded train station. You cannot record every sound forever at full quality. You need a way to recognize which snippets might contain the sentence you care about. But if your filter is too strict, you may throw away the clue. If it is too loose, you drown in noise. LHCb's trigger and data acquisition systems are part of this balancing act. They are not glamorous in the way a new particle announcement is glamorous, but they are essential. A rare decay that is never recorded might as well never have happened, at least for the purpose of measurement. Once the data are saved, the visible work is still only beginning. Events must be reconstructed. Tracks must be fitted. Particle identities must be assigned. Possible B meson candidates must be built from combinations of final state particles. Backgrounds must be estimated. Control samples must be studied. A control sample is a process that is similar enough to test the analysis, but well understood enough that it provides a check. If the detector and reconstruction behave properly in the control sample, physicists gain confidence that they understand the response in the rarer signal channel. If not, they go back and find out why. This is the unglamorous heartbeat of precision science. The search for rare B-meson decays depends on this rhythm. A possible signal is never taken at face value. It is surrounded by questions. How likely is it that random combinations of particles imitate the decay? How much background comes from other B decays with missing particles? How often are hadrons misidentified as leptons? How accurately does the simulation reproduce the detector response? How stable are the results if the data are divided by time period, detector region, or event type? A real effect should survive these checks. A fragile effect may disappear when the analysis is improved. This is why the phrase impossible decays needs careful handling. The decays are not impossible in the sense that they cannot happen at all. Many are allowed by the standard model, but they are rare, suppressed, or tightly predicted. Others would be forbidden or extremely unlikely without new physics. The detector is listening for decays that are impossible only in the softer dramatic sense. Outcomes that should not appear in a certain pattern if the known rules are complete. It listens for the slightly wrong rate, the unusual distribution, the comparison that does not settle where expected. In particle physics, impossible often arrives wearing the modest clothing of improbable. LHCb is particularly suited to this because beauty particles are its specialty. Other great experiments at the Large Hadron Collider look broadly for many kinds of high-energy phenomena. LHCb looks closely at the behavior of particles containing beauty and charm quarks. It is a precision instrument for flavor physics, for matter-antimatter differences, for rare decays, and for the subtle signs of physics beyond the standard model. If the universe hides new physics not as a massive object produced directly, but as a small alteration in how known particles decay, then LHCb is one of the places most likely to notice. There is something almost detective-like about its work, but not the noisy kind of detective who bursts through a door in the final scene. More the patient sort who notices that the ashtray has been moved half an inch. A beauty meson decays into certain particles. The rate is measured. The same kind of decay involving electrons is compared with the one involving muons. A channel involving tau leptons is studied with all the extra difficulty that taus bring. A distribution of angles is checked. A rare branching pattern is counted. Each result is placed beside the standard model. Most agree. Some have not agreed as comfortably. The detector does not explain the mystery by itself. It provides the evidence from which explanations must be built. The human side of this is easy to miss. Behind every published result are many people working across years. Physicists, engineers, technicians, software experts, students, and analysts all contribute to the detector and the interpretation of its data. Someone designs a sensor. Someone studies how radiation affects it. Someone writes code that reconstructs tracks. Someone checks whether a calibration constant shifted during a run. Someone spends months understanding a background that will appear as a small shaded region on a plot. By the time the public hears that a result is interesting, it has already passed through an enormous amount of invisible labour. And that labour has to be cautious because the stakes are high. A confirmed violation of lepton universality would be extraordinary. It would mean the standard model is missing something in the way quarks and leptons interact. But extraordinary claims do not become true because they are exciting. They become credible because the detector is understood, the analysis is robust, the uncertainties are honest, and independent measurements point in the same direction. LHCb's job is not to make the universe more dramatic. It is to make the measurement more reliable. This is why upgraded detectors matter so much. More data alone is helpful, but better data can be even more powerful. Improvements in tracking, readout, timing, and particle identification allow physicists to study rarer processes and reduce uncertainties. They also allow checks that were previously difficult. If an anomaly is real, sharper instruments should make it clearer. If it is caused by some subtle experimental issue, sharper instruments may expose that too. The upgraded LHCb experiment is therefore not simply continuing the same work with a larger bucket. It is listening with a more refined ear. One can imagine the detector as a long layered memory of a collision. First, the protons meet, then short-lived particles appear. A meson travels a tiny distance and decays. Charge tracks spread through the vertex detector and tracking stations. A magnet bends them. Light appears in Cherenkov detectors. Energy showers bloom in calorimeters. Muons continue outward. Electronics convert physical traces into data. Software reconstructs the event. Analysts test whether the pattern matches a known decay. Finally, after many such events, a number emerges. Not a single dramatic image, but a measured probability, a comparison, a deviation perhaps, a whisper. The remarkable thing is that this chain can connect a microscopic decay to some of the largest questions in physics. Does the weak force treat leptons equally? Are there undiscovered particles that connect quarks and leptons? Could a hidden force influence beauty meson decays? Is the pattern of particle generations a clue to deeper structure? Is dark matter part of a hidden sector that also leaves traces in flavor physics? These questions sound grand, almost too grand for such tiny evidence. But this is how particle physics often works. A small decay becomes a window because the rules governing it are so precise. When LHCb listens for impossible decays, it is really listening for inconsistency. Not chaos, not magic, not anything outside reason. Just a place where the known theory does not quite match the measured world. A decay that happens too often. Another that happens too rarely. A muon channel that appears different from an electron channel. A tau result that sits above expectation. Each inconsistency may fade. Some already have softened with improved analysis. But each one is taken seriously because, if it survives, it could show where the standard model gives way to something wider. That is the beauty of the detector's role. It does not need to know in advance what new physics looks like. It only needs to measure known processes well enough to notice when they are not quite known. The theories can come afterward. Leptoquarks, new bosons, hidden forces, dark sectors, deeper symmetries. These are possible explanations, not assumptions built into the machine. LHCb records what particles do. It does not force them into a preferred story. So, beneath the ground, the experiment continues its quiet work. It watches collisions and reconstructs decays. It separates tracks born at the primary collision point from those born a little later. It distinguishes electrons from muons, kaons from pions, signal from background, and persistent patterns from statistical accidents. It does this not once, but millions and millions of times, because the truth of a rare process is not found in a single event. It is found in the accumulation. The patient counting, the repeated check, the refusal to be fooled by the first interesting shape in the data. And once the detector has listened, the next question is how to interpret what it heard. A small deviation can be thrilling, but it can also be treacherous. It might be the first sign of a new particle, or it might be a statistical fluctuation. It might reveal a hidden force, or it might reveal an underestimated background. It might point beyond the standard model, or it might remind us that even our best instruments require constant humility. The detector can bring the whisper to the surface, but deciding whether it is a message from new physics or merely noise shaped like meaning requires another kind of patience entirely. The difficult thing about a whisper in the data is that it can come from several places. It might be the first faint sound of something real, something new, something pressing gently against the walls of known physics. It might also be the sound of chance, or it might come from the instrument itself, from the complicated business of measuring particles that exist for almost no time at all before they scatter their clues through layers of metal, silicon, magnets, electronics, and code. Before anyone can say that nature has revealed a deeper rule, physicists have to ask a quieter and much less glamorous question. Could we be fooling ourselves? This is not a small question. In fact, it is one of the most important questions in all experimental science. The universe does not hand over truth in a neat envelope. It gives signals mixed with noise, patterns mixed with accidents, and rare events mixed with ordinary events that happen to look similar. A particle detector is not a magical window into reality. It is a machine, a very advanced and beautiful machine, but still a machine, and every machine has limits. It sees some things more easily than others. It has regions where it performs better, periods when conditions change, and processes that must be corrected for with great care. So when the data seem to show that electrons and muons are not behaving quite as expected in B-meson decays, the first response is not simply excitement, it is suspicion, discipline, and a long list of checks. A statistical fluke is the simplest possibility to imagine, though not always the simplest to dismiss. Particle physics deals in probability. The standard model does not say that every single B-meson must decay in a fixed visible way, like a train arriving at a scheduled platform. It says how often different outcomes should happen over many events. If you only watch a small number of decays, the pattern may wobble. That is normal. Flip a coin 10 times, and you might get 7 heads. That does not mean the coin has abandoned fairness. It may just be chance doing what chance does. Flip it 10 million times, and the balance should become much clearer. Particle physics is full of these coin tosses, except the coins are unstable quantum systems, the tosses are subatomic decays, and the table is an underground detector with more cables than anyone should have to think about before bedtime. When a measurement differs from expectation, physicists ask how surprising that difference really is. Is it the kind of variation that could happen naturally if the standard model is correct? Or is it so unlikely that something else may be required? This is where statistics enters the story, not as a dry technical detail, but as the language of caution. A small deviation may look interesting on a plot, but if it could easily arise from random variation, it cannot carry much weight. A larger deviation may be harder to ignore, but even then, particle physicists have learned to be careful. The history of the field contains many hints that appeared promising and later faded as more data arrived. The universe is subtle, but data can be mischievous. There is a phrase sometimes used in science, the look elsewhere effect. The idea is simple. If you search in many places, you increase the chance of finding something unusual somewhere, even if nothing genuinely new is happening. Imagine walking through a large hotel and listening at every door. Eventually you may hear a strange noise from one room. That does not necessarily mean you have discovered a secret laboratory. It may simply mean that in a hotel with enough rooms, someone eventually drops a suitcase. In particle physics, if experiments examine many decay channels, many mass ranges, many distributions and many comparisons, a few of them may naturally look odd just by chance. The important question is whether the oddness persists when more data arrive and when the test is repeated in independent ways. This is one reason the B-meson anomalies have been so carefully watched over time. A single strange measurement would have been interesting but fragile. A pattern across several related measurements is harder to dismiss but still not decisive. Some earlier hints involving electron and muon comparisons became less tense after improved analysis. That matters. It tells us that at least part of the earlier unease may have come from the difficulty of the measurement, or from the limited data, or from a statistical fluctuation that softened as the picture sharpened. This does not make the scientists wrong for being interested. It makes them right for checking. A hint is not a promise. It is an invitation. Measurement error is another possible explanation, though the phrase can sound too blunt. It may suggest someone simply made a mistake, like writing down the wrong number or plugging the kettle into the toaster, which is not generally recommended. But in precision physics, measurement error often means something more subtle. It can mean the detector response was not modelled perfectly. It can mean the background estimate needed refinement. It can mean the efficiency for identifying electrons was slightly different from what was assumed. It can mean the simulation did not reproduce some small feature of the real apparatus. These are not embarrassing failures. They are the natural challenges of measuring extremely rare processes in an environment full of complicated events. Consider the electron again. It is light, charged, and energetic in ways that make it both useful and difficult. As it passes through detector material, it may radiate energy. Its signal can spread into showers. Some of that energy must be recovered. Some of it may be lost or mismeasured. The muon, by contrast, often passes through the detector more cleanly and reaches the outer muon chambers, leaving a track that is easier to identify. If you are comparing B-meson decays involving electrons with those involving muons, this difference is not a minor inconvenience. It is central. The detector itself treats electrons and muons differently, because electrons and muons interact with the detector differently. The challenge is to remove the detector bias so that the comparison reveals nature, not machinery. This is why physicists use control measurements. A control measurement is like checking your thermometer in ice water and boiling water before trusting it to tell you whether soup is warm enough. In a particle experiment, analysts study processes that are well understood and similar to the signal being measured. If the detector reconstructs those known processes correctly, confidence grows. If not, something in the analysis must be fixed. These control studies are essential because rare B decays cannot be understood in isolation. The experiment has to prove that it can see electrons and muons properly in situations where the answer is already expected. Only then can it ask whether a rare decay is truly strange. Backgrounds are another source of trouble. In collider physics, a background is an ordinary process that imitates the signal. The detector may record particles that look as though they came from a rare B-meson decay, when in fact they came from a more common process arranged in a misleading way. Sometimes a particle is misidentified. Sometimes part of the event is missing. Sometimes two unrelated tracks accidentally combine into something that resembles a B-meson candidate. Nature is very good at producing clutter. The experiment has to sort through that clutter and decide how much of the apparent signal is genuine. This is not done by guesswork. Analysts use data-driven methods, simulations, side regions of distributions, and known decay modes to estimate how much background is present. They test whether the shapes match. They check whether the result changes if selection criteria are loosened or tightened. They divide the data into different periods and detector regions. They ask whether the same effect appears where it should and disappears where it should not. If an anomaly is real, it ought to survive these tests. If it is an artifact, it may shift, shrink, or vanish when the analysis is changed. There is also the problem of theory uncertainty. The standard model prediction is not always a single, perfectly sharp number handed down from a mountain. Some predictions are extremely clean. Others depend on the behavior of quarks bound inside mesons, where the strong force becomes complicated. Quarks are never isolated inside ordinary matter. They are held together by gluons in a restless quantum environment. Calculating the details of B-meson decays can therefore be difficult. In some lepton universality ratios, many strong force uncertainties cancel, which is why those ratios are so valuable. But in other observables, especially absolute decay rates or angular patterns, the theory side has its own uncertainties, so a mismatch may reflect new physics, but it may also reflect the difficulty of calculating the old physics precisely enough. This is a delicate point. When people hear that an experiment disagrees with theory, they may imagine the experiment is solid and the theory is clearly wrong. But the comparison depends on both sides. The measurement has uncertainty. The prediction may have uncertainty. If the two do not line up, the cause could be in the data, in the calculation, or in nature itself. The work is to narrow those possibilities. A true anomaly becomes more convincing when the experimental measurement is robust. The standard model prediction is clean, and related measurements point in a coherent direction. The B-meson puzzle has been compelling because some of the relevant comparisons are designed to be clean tests. Comparing electron and muon channels in related decays can reduce many theoretical uncertainties. That is why earlier hints of lepton universality violation attracted so much attention. If electrons and muons appeared differently in a ratio where the standard model prediction was especially reliable, the implication would be hard to ignore. Yet because the experimental treatment of electrons and muons is different, even a clean theoretical test remains an experimental challenge. Clean does not mean effortless. It means that if everything is measured correctly, the interpretation is sharper. Now we come to the most exciting possibility, which must be handled with the greatest care. Perhaps the anomaly is not a fluke. Perhaps it is not a detector effect. Perhaps the uneven behavior in certain B-meson decays is the first indirect sign of something deeper. If that is true, then the small mismatch would be more than a measurement problem. It would be a message from beyond the standard model. What could that deeper thing be? One possibility is a new particle that affects the decay without being directly seen. In quantum physics, particles can influence processes indirectly. A new heavy particle might be too massive to appear clearly in the detector, or too rare to stand out as a direct discovery, but it could still alter the probability of a B-meson decay. It could make a muon channel slightly more or less likely. It could affect Taus more strongly than electrons. It could change angular patterns or branching rates. The visible particles would be familiar, but their proportions would carry the imprint of something unfamiliar. A leptoquark is one of the most discussed possibilities. Such a particle would connect quarks and leptons, two families that the standard model keeps distinct in ordinary interactions. Since B-mesons contain beauty quarks, and the anomalies involve leptons, a leptoquark feels like a natural suspect. It could provide a new route for certain decays, altering the rates in ways that depend on which lepton is involved. The idea is attractive because it speaks directly to the structure of the anomaly. If the data suggest a link between quark flavor and lepton flavor, a particle that links quarks and leptons is worth considering. Another possibility is a new force carrier, often called a Z-prime boson in the language of physics. Spoken gently, it is a hypothetical heavier cousin of known neutral weak force particles. If such a particle existed, and if it interacted differently with muons than with electrons, it could shift the decay patterns of B-mesons. It might not be easy to produce directly, but its influence could appear as a small deviation in rare processes. This is one of the powerful ideas behind precision physics. You do not always need to see the new thing directly. Sometimes you can see the shadow it casts on familiar behavior. There are darker and more hidden possibilities too. Some theories connect flavor anomalies to dark matter or to hidden sectors, regions of particle physics that interact only weakly with the particles we know. Dark matter is inferred from its gravitational effects in the universe, but we do not yet know what it is made of. If dark matter belongs to a richer hidden world, perhaps some mediator particle links that world to ordinary quarks and leptons. B-meson decays could then become a rare doorway where the hidden and visible sectors nearly touch. That is speculative, of course, but speculation guided by data is part of how theory explores the unknown. The difficulty is that new physics cannot simply explain one anomaly and ignore everything else. A proposed leptoquark or new force must survive many constraints. It must not create effects in other decays that experiments have already ruled out. It must fit with collider searches. It must not disturb precision measurements that agree beautifully with the standard model. It must explain the pattern without making the rest of physics fall apart. This is harder than it sounds. The standard model is not easy to improve because it is so successful. Adding something new is like adding a room to a house where every wall, pipe and wire is already carefully connected. You may solve one problem and create 5 leaks. This is why theorists often speak in terms of allowed regions and constraints. They're not simply inventing particles and asking whether they sound nice. They calculate what those particles would do in many different settings. If a leptoquark explains a B-meson anomaly, what else should it affect? If a new boson couples to muons, should it appear in other muon-related measurements? If a hidden force changes beauty quark decays, what happens in strange quark decays, charm decays, or high-energy collisions? The more places a theory survives, the more interesting it becomes. The more places it fails, the more gently it is escorted out of the room. There is a useful lesson here about scientific uncertainty. Uncertainty is not ignorance in the lazy sense. It is a measured space of possibilities. When physicists say they do not yet know whether an anomaly is a fluke, a measurement issue, or new physics, they are not shrugging. They are mapping the uncertainty. They are identifying what needs more data, what needs better calibration, what needs improved theory, and what related processes should be checked. The unknown becomes structured. It becomes a research program. This is why the future of the B-meson puzzle depends on accumulation. More data will reduce statistical uncertainty. Improved detector understanding will reduce experimental uncertainty. Better theoretical calculations will sharpen standard model predictions. Independent measurements will test whether the same pattern appears elsewhere. If an anomaly is a statistical fluctuation, more data usually causes it to drift back toward expectation. If it is a measurement problem, improved methods may reveal and correct it. If it is new physics, it should become more coherent, appearing in related observables in ways that match a deeper explanation. The suspense comes from the fact that all three possibilities have happened before in science. Flukes have faded. Measurement problems have been corrected. Deep discoveries have emerged from small mismatches. Mercury's orbit did not quite match Newtonian gravity, and eventually general relativity explained why. Certain radioactive processes revealed the weak interaction. Precision studies of particles have pointed toward hidden structure before, but many anomalies have also vanished, leaving behind better methods and humbler expectations. The B-meson story sits in this tradition, not yet resolved, not empty, and not safe to exaggerate. It is tempting to want the dramatic answer, something deeper. Of course we do. A new particle, a hidden force, a doorway beyond the standard model. These are thrilling ideas. But the discipline of physics lies in letting the data earn that drama. The beauty of the process is that nature cannot be hurried by our preferences. If the anomaly is real, it will remain as the measurements improve. It will connect with other results. It will become harder to explain away. If it is not real, it will fade, and that fading will still teach physicists how to measure rare decays more accurately. For now, the honest answer is that the possibility remains open in parts of the wider flavor puzzle. Some earlier electron and muon tensions have softened. Some B-decay measurements involving tau leptons remain interesting. Other rare processes continue to be tested. The landscape has changed, but the question has not disappeared. Are the patterns in B-meson decays simply statistical accidents and experimental difficulties, or are they the first traces of a hidden layer in nature? The answer may come slowly. It may come from LHCb with more data. It may come from another experiment studying related decays. It may come from a direct search that finds a new particle, suddenly turning old anomalies into clues that were waiting to be understood. Or it may come from the quiet disappearance of the tensions, leaving the standard model standing stronger than before, still incomplete, but not cracked in this particular place. And that is where the mystery becomes especially interesting. Because every option changes the story. A fluke teaches caution. A measurement error teaches precision. A deeper effect teaches us that the known particles are not the whole cast. The B-meson does not tell us which answer to choose yet. It simply decays again and again while the detectors listen and the physicists count. So we remain in the patient middle ground, which is where much of science actually lives. Not certainty, not confusion, but disciplined curiosity. The data have whispered. Some whispers have faded. Others still invite attention. The standard model remains powerful, but not final. And in the space between a statistical accident and a new force of nature, theorists have begun to assemble their suspects. each one strange, each one constrained, each one trying to explain why a beauty meson might decay, as though something unseen were leaning gently on the rules. A careful grounding point before the narration continues. CERN reported that improved rare beauty meson tests using the full first and second Large Hadron Collider data samples agreed with the standard model and superseded earlier hints in those specific electron and muon comparisons, while the wider family of beauty meson flavor puzzles continues to motivate tests of possible new particles such as leptoquarks and heavier neutral force carriers. Once a strange pattern appears in the data, even a small one, the imagination of physics begins to populate the darkness with suspects. Not suspects in the criminal sense, of course. No leptoquark has been seen sneaking away from the detector wearing a tiny hat and looking guilty, though one feels that if it had, the analysis note would still be written with careful understatement. These suspects are possible explanations. They are proposed additions to the known rules, ideas that might account for why certain beauty meson decays appeared, at least in some measurements, to lean away from what the standard model expected. They are not confirmed particles. They are not discoveries waiting politely in a queue. They are hypotheses, and in physics a hypothesis must do more than sound interesting. It must survive contact with data. The first suspect often mentioned is the leptoquark. The name is wonderfully direct once you understand it. A leptoquark would be a particle that connects leptons and quarks. Leptons include electrons, muons, taus, and neutrinos. Quarks are the ingredients inside protons, neutrons, mesons, and many other particles. In the standard model, these two families of matter are distinct. They both take part in interactions, and they both belong to the same broad particle world, but there is no ordinary particle whose role is simply to link a quark directly with a lepton in the way a leptoquark would. So when an anomaly appears in a decay involving a beauty quark on one side and leptons on the other, leptoquarks naturally walk into the conversation, clear their throats, and look suspiciously relevant. A beauty meson contains a beauty quark. When it decays, that beauty quark can change into another kind of quark, and the decay may also produce leptons such as electrons, muons, or taus. If the observed pattern suggests that different leptons are not being treated equally, then a particle that connects quarks and leptons could, in principle, alter the process in a lepton-dependent way. It might make a muon channel less likely or more likely. It might affect tau channels more strongly. It might create a pattern that looks like lepton universality is being bent, not because the weak force itself has suddenly become unfair in its ordinary form, but because an additional interaction has entered the scene. This is what makes the leptoquark idea so attractive. It speaks the language of the anomaly. The anomaly is about quarks changing in the presence of leptons. The leptoquark is a proposed bridge between quarks and leptons. If one were writing a mystery novel, this would be the character whose muddy boots match the footprints near the garden gate. But science is not satisfied by matching boots. It wants to know the size of the mud particles, whether the character had time to be there, and whether 3 other witnesses saw the same boots in a completely different town. A leptoquark model must explain the beauty meson measurements without contradicting other experiments that have searched for leptoquarks directly or indirectly. That is a difficult requirement. One reason it is difficult is that leptoquarks, if they exist, would not usually be shy in only one place. Depending on their mass and couplings, they might be produced in high-energy collisions. They might affect other rare decays. They might influence processes involving charged leptons in ways that have already been measured very precisely. So, a proposed leptoquark cannot simply be adjusted to fix one beauty meson result, and then vanish whenever other data look in its direction. It must be consistent across the landscape. It must help where help is needed, and remain quiet where experiments already agree with the standard model. This balancing act is one of the reasons theory papers can become long, dense, and very determined, like legal contracts written for particles. Different types of leptoquarks can be imagined. Some are scalar, meaning they have no intrinsic spin in the sense used in particle physics. Others are vector, meaning they behave more like force-carrying particles in certain respects. Some couple more strongly to particular generations of matter. Some prefer muons, some taus, some combinations of quarks and leptons that would produce different patterns in different decays. The details matter enormously. A leptoquark that explains one set of anomalies may fail another test. Another might survive current limits, but predict signals that future experiments can seek. In this way, the leptoquark is not one suspect, but a family of suspects, all sharing the same general idea but each with its own alibi, motive, and inconvenient paperwork. Then there is the Z-prime boson. Spoken aloud, it sounds almost like the name of a quiet robot from an old science fiction film, but the idea is straightforward enough. The standard model already contains force-carrying particles associated with the weak force. A Z-prime boson would be an additional heavy neutral particle, connected to a new force or an extension of the known electroweak structure. It would not be the same as the known Z boson, but it would resemble it in the broad sense of being a neutral mediator of interactions. If it existed, it could influence rare beauty meson decays by adding a new path through which the process can occur. A Z-prime boson becomes interesting for the beauty meson puzzle if it interacts differently with different leptons. Suppose it couples more strongly to muons than electrons, or to certain quark transitions involving beauty and strange quarks. Then it could shift the rates of rare decays involving muons without doing the same thing to electrons. That would create exactly the kind of lepton imbalance that early measurements seem to suggest. Again, this does not mean such a particle has been found. It means that if the anomaly were real, a Z-prime boson could be one possible explanation. The appeal of this idea is that forces are familiar in physics. We understand many interactions in terms of particles that mediate them. Electromagnetism has the photon. The weak force has its own carriers. The strong force has gluons. So if nature contains another force, perhaps one that is heavy, short range, or connected only to certain particles, then a new carrier is a natural way to describe it. A Z-prime boson would be a sign that the known forces are not the whole story. It would mean the standard model is part of a wider structure, one with an additional interaction that has remained hidden, because it is subtle, heavy, weakly coupled, or all three. But the Z-prime suspect also faces strict questioning. If such a boson interacts with muons, then it may affect other muon processes. If it interacts with quarks, it may influence the mixing of neutral beauty mesons with their antimatter partners. If it is not too heavy, direct searches at colliders may be able to produce it. If it is very heavy, its indirect effect becomes smaller and must still be large enough to explain the anomaly. This creates a narrow path. The particle must be strong enough to matter, but not so strong that it would already have been seen somewhere else. In the language of a quiet evening, it has to leave footprints in one patch of snow while somehow not disturbing the rest of the garden. This is why many Z-prime models are carefully shaped. They may assign the new force to particular combinations of particle generations. They may couple more strongly to muons than to electrons. They may prefer the second and third generations of matter, which would be particularly interesting because ordinary matter around us is made mostly from the first generation. If the hidden force speaks mainly to heavier, less familiar particles, that might explain why it has remained difficult to detect in everyday matter and in many older experiments. It would be a force not of the ordinary world of atoms, but of the heavier families that appear in cosmic rays, accelerators, and brief unstable decays. That possibility leads into a larger thought. Perhaps the three generations of matter are not merely copies with different masses. Perhaps they are arranged by a deeper principle. The electron, muon and tau look like three versions of a similar particle, but with very different masses. The quarks also come in generations. The first generation builds ordinary matter. The second and third appear in short-lived particles produced in high-energy processes. The standard model describes this pattern, but it does not explain why nature chose it. A new force that distinguishes among generations could be a clue. It would suggest that the family structure of matter has hidden architecture. The beauty meson anomalies have often been discussed in exactly this context. They might indicate that the heavier generations, the muon, the tau, the beauty quark, and perhaps others, are more deeply connected than we realized. It is as though the standard model presents a seating chart, but not the reason everyone is sitting where they are. A leptoquark or a Z-prime boson might reveal that certain seats are connected by invisible threads. Tug one thread in a beauty meson decay, and a muon channel shifts. Tug another, and a tau process changes. The pattern, if real, could point toward a deeper rule behind flavor. Flavor, as we've said, is the physicist's word for the different types of quarks and leptons. It is one of the strangest open puzzles in particle physics. Why are there 6 quarks arranged in 3 pairs? Why are there 3 charged leptons? Why do their masses span such enormous ranges? Why do quarks mix with one another in one pattern, while neutrinos mix in another? Why does matter dominate over antimatter in the observable universe? These questions may seem separate, but they all brush against the same mystery. The standard model gives us an excellent description of what happens. It is much less satisfying when asked why the pattern is what it is. Hidden forces are another broad category of suspect. A hidden force is not a single specific theory, but a general idea that there may be interactions beyond the known ones, perhaps acting mainly on particles we do not usually observe. The force might be connected to a hidden sector, a collection of particles that interact weakly with ordinary matter. This is especially intriguing because dark matter already tells us that something unseen exists in the universe. We know dark matter is there through gravity, through the motion of galaxies, the structure of cosmic web, and the bending of light around massive objects. But we do not know what dark matter is made of. If dark matter belongs to a hidden sector, perhaps that sector has its own forces, its own particles, and its own internal structure. Could such a hidden sector connect to beauty meson decays? Possibly, though the details vary widely from one theory to another. A hidden force might not show itself by producing visible particles directly. It might appear through small changes in decay rates, or through missing energy carried away by invisible particles. It might interact through a mediator, a particle that acts as a bridge between ordinary matter and the hidden world. If that mediator couples differently to electrons, muons, or taus, it could contribute to the same kind of lepton non-universality that made the anomalies interesting in the first place. This is where the story becomes wider than B mesons alone. A tiny decay in a collider could, in some theories, connect to the dark matter problem. That does not mean it does. It means that the same desire to find physics beyond the standard model links many different questions. The missing matter in galaxies, the masses of particles, the imbalance between matter and antimatter, the puzzle of flavor, and rare decay anomalies may or may not share a common cause. Physicists do not know. But when a possible anomaly appears in a sensitive place, theorists naturally ask whether it can be part of a larger pattern. A good new theory is not merely a patch, it is a map. There are other suspects too. Some models involve extended Higgs sectors, where the particle associated with giving mass to other particles is not alone, but part of a larger family. Such models can sometimes affect decays involving heavier particles, especially taus. Others involve supersymmetry, an elegant but so far unconfirmed idea that every known particle has a heavier partner. Supersymmetric particles could, in some cases, influence rare decays indirectly. There are theories with extra dimensions, where the geometry of space itself is richer than it appears at ordinary scales. There are composite models, in which particles we call fundamental might themselves have deeper structure. Each idea brings its own possibilities, constraints, and experimental signatures. Yet it is worth keeping the mood calm. When a field has many possible explanations, That does not mean nature is overflowing with confirmed new particles. It often means the data are not yet decisive enough to choose among them. A vague shadow can be made to resemble several different animals if the light is dim. More data make the shape clearer. Some models fall away, others become more strained. A few remain plausible. The work of theory is not just to invent suspects, but to make predictions that can be tested. If a leptoquark explains one anomaly, it may predict a related decay that should appear at a certain rate. If a Z-prime boson explains another, it may produce a signal in muon pairs or affect neutral meson mixing. If a hidden sector is involved, it may imply invisible decay products or correlations with dark matter searches. This is why future measurements are so important. A real new interaction should not appear only as one isolated irregularity. It should have consequences. Perhaps it changes beauty meson decays involving Taus. Perhaps it alters rare strange particle decays. Perhaps it appears in high-energy collision searches. Perhaps it produces lepton flavor violating decays, where one lepton type transforms into another in a way the standard model strongly suppresses or forbids. These related searches are like asking the suspect where they were on several different nights. A true culprit leaves a trail. A coincidence does not. At the same time, the fading of some earlier electron and muon anomalies has made the suspect list more cautious. When improved rare beauty meson measurements agree with the standard model, certain explanations lose urgency or must be reshaped. A model built mainly to explain a vanished tension may no longer be needed. But if other tensions remain, especially those involving tau leptons, some versions of these ideas can still be relevant. The field adapts. It does not cling blindly to the most exciting old interpretation. It asks what the newest data require. This adaptation is a strength. It prevents physics from becoming storytelling without accountability. A leptoquark is fascinating, but it must earn its place. A Z-prime boson is elegant, but elegance is not evidence. A hidden force could explain many things, but could is not the same as does. Theories live under pressure from measurement. They are trimmed by constraints, reshaped by new results, and sometimes abandoned when the universe refuses to cooperate. There is no shame in that. A failed theory can still teach us where not to look, or how to build a better one. Still, one can understand why these suspects are so compelling. The standard model is complete enough to be powerful and incomplete enough to be frustrating. It describes the known particles beautifully, but it leaves too many questions unanswered for physicists to believe it is the final story. Something beyond it almost certainly exists. The mystery is where. It may be at energies far beyond our current colliders. It may be in dark matter. It may be in neutrinos. It may be in the early universe. Or it may be hiding in small deviations in flavor physics, in the rare decays of particles that live too briefly for us to notice without machines like the Large Hadron Collider beauty experiment. The beauty meson anomalies are therefore part of a broader search strategy. Instead of only trying to create new particles directly, physicists also study known particles with extreme precision. If a new particle is too heavy to produce, it can still influence familiar processes indirectly. This is like noticing a planet before seeing it, because the motion of another body is slightly disturbed. The unseen thing reveals itself through its effect on the seen. Rare decays are ideal for this because the standard model contributions can be small, making new effects easier to notice if they exist. But every suspect must answer the same hard question: why here? Why would new physics show up in beauty meson decays and not already in thousands of other measurements? A plausible answer often involves flavor structure. The new interaction might prefer certain generations. It might couple weakly to ordinary first-generation matter, but more strongly to heavier particles. It might be arranged so that it affects beauty quarks and muons or taus, while avoiding tight constraints from electrons and light quarks. Such patterns may sound artificial, but they may also hint at a real organizing principle. After all, the standard model itself contains unexplained patterns in masses and mixings. What looks artificial today may be a clue to tomorrow's deeper theory. There is a quiet irony here. The particles most absent from ordinary life may be the ones that explain ordinary life most deeply. Beauty quarks do not sit inside stable atoms. Muons decay quickly. Taus vanish almost as soon as they appear. Leptoquarks and Z-prime bosons, if they exist, would be even more remote from daily experience. And yet these fleeting or hypothetical particles may hold clues to why matter has families, why forces have the forms they do, and why the universe is made of something rather than nothing. The ordinary world rests on rules written in a language whose full grammar we do not yet know. So the suspect list remains open. Leptoquarks offer a direct bridge between quarks and leptons. Prime bosons suggest a new force carrier, perhaps one that favours certain generations. Hidden forces point toward sectors of nature not yet visible, perhaps even connected to dark matter. Extended Higgs models, supersymmetry, compositeness, and other frameworks linger nearby, each trying to explain how a small crack in beauty meson data might fit into a larger architecture. Some will fail. Most probably will. That is normal. In science, many suspects are questioned before the right answer is found, and sometimes the answer is that no crime occurred in the first place. But if one of these suspects is real, the implications would be enormous. A confirmed leptoquark would change the relationship between matter families. A confirmed Z-prime boson would reveal a new force. A hidden sector connection could link collider physics with the dark matter problem. Any of these would mean the standard model is not merely incomplete in the abstract, but incomplete in a way we can measure. It would give physicists a foothold beyond the known theory, a first step into a larger structure. For now, the suspects remain in the room, but none has confessed. The data are not yet strong enough to choose. Some earlier clues have softened. Others continue to invite attention. The detector keeps listening. The theorists keep testing possibilities against every available constraint. The standard model remains standing, slightly mysterious, remarkably durable, and still surrounded by questions it cannot answer on its own. And so the story moves from the suspects themselves to the doorway they might open. Because the real excitement is not merely that a leptoquark or a new boson could exist. It is what such a discovery would mean for the entire structure of physics. If beauty meson's decays are truly pointing beyond the standard model, then the anomaly is not just a strange result in one experiment. It is a signpost toward a deeper layer of nature, one where the familiar particles are part of a larger pattern, and the forces we know may be only the visible edges of something wider. If one of the suspects were real, if a leptoquark, a heavier neutral force carrier, or some hidden interaction were truly leaning on the decays of beauty mesons, then the result would not simply add a new item to a particle list. It would open a doorway beyond the standard model. That phrase is used so often in particle physics that it can begin to sound almost ordinary, like a sign on a university corridor. Beyond the standard model, third door on the left, please knock before entering. But the meaning is enormous. It would mean that the most successful theory ever built to describe elementary particles is not the whole map. It would mean that one of its quiet assumptions has met the edge of its territory. The standard model is not a flimsy theory waiting to be replaced by the next exciting idea. It is sturdy, precise, and extraordinarily successful. It describes the known elementary particles and the electromagnetic, weak, and strong interactions that govern them. It explains how quarks bind into protons, neutrons, mesons, and other composite particles. It describes how electrons interact with light, how neutrinos participate in weak processes, how particles can change identity through weak interactions, and how the Higgs field gives mass to elementary particles in the theory. Its predictions have been tested in countless experiments. Some of those tests are so precise that the agreement between theory and measurement feels almost unreasonable, as though nature and mathematics have been quietly corresponding behind our backs. This is why a possible failure matters so much. If a weak theory fails, no one is surprised. If a rough guess fails, it simply becomes a better guess later. But when the standard model shows even a small discomfort, the discomfort matters because the model is so good almost everywhere else. A tiny mismatch in a weakly tested idea is interesting. A tiny mismatch in a highly tested structure can be profound. It is a little like finding a single locked drawer in a library where every other cabinet has opened perfectly for 50 years. You do not assume the library is useless. You become very interested in the drawer. The beauty meson anomalies, if real, would point to such a drawer. They would not necessarily overthrow the entire standard model. That is not how modern physics usually works. Newtonian physics was not thrown into the sea when Einstein arrived. It remained an excellent approximation for ordinary speeds and everyday gravity. General relativity did not make Newton foolish. It showed where Newton's picture was incomplete. In the same way, a confirmed anomaly in B meson decays would likely reveal the standard model as part of a larger framework, valid in many situations but not final. The old theory would remain useful, accurate and essential, but it would be nested inside something deeper. The doorway beyond the standard model has been expected for a long time, even without the B meson puzzle. Physicists already know the standard model leaves major questions unanswered. It does not explain dark matter, the invisible mass that appears to shape galaxies and cosmic structure through gravity. It does not include gravity as a quantum force. It does not explain why the universe contains so much more matter than antimatter, even though the early universe should have produced both in closely related amounts. It does not explain why the masses of particles have the values they do. It does not explain why there are 3 generations of matter with the electron, muon and tau forming one repeating pattern and the quarks forming another. It describes the structure, but it does not fully explain the architecture. That is why physicists search in many directions at once. Some experiments look directly for new heavy particles by creating high-energy collisions and studying what emerges. Some search for dark matter particles passing quietly through underground detectors. Some study neutrinos, which are already known to behave in ways that required physics beyond the original standard model. Some watch the cosmos, looking at the afterglow of the early universe, the distribution of galaxies, and the behavior of gravity on the larger scales. Others, like LHCb, study rare decays with extraordinary precision, hoping that unknown physics will show itself not as a new object appearing openly, but as a slight change in how known particles behave. This indirect route is powerful because new physics may be beyond direct reach. A new particle might be too massive to produce in large numbers at the current collider energy. It might interact too weakly to stand out clearly. It might decay in ways that are difficult to reconstruct. But even if it cannot be seen directly, it may still influence known processes. In quantum physics, heavy or hidden particles can affect probabilities. They can alter rare decays slightly, changing how often a beauty meson produces one set of particles rather than another. They can leave fingerprints without leaving the whole hand. That is the doorway flavor physics offers. Flavor physics studies the different types of quarks and leptons and how they change. The word flavor may sound gentle, almost kitchen-friendly, but the field is one of the most sensitive probes of hidden structure. The standard model contains a pattern of particle generations. The first generation includes the particles that make ordinary matter, such as up and down quarks and electrons. The second and third generations include heavier relatives, such as charm and strange quarks, top and beauty quarks, muons, and taus. These heavier particles are unstable, appearing in high-energy collisions and decays rather than forming the world around us. Yet they may hold clues to why the ordinary world exists as it does. The standard model tells us how these particles behave, but not why the pattern is arranged this way. Why does the electron have a heavier cousin called the muon, and an even heavier cousin called the tau? Why do quarks come in 6 kinds? Why do their masses differ so dramatically? Why do quarks mix with one another in weak interactions according to a particular pattern? Why do neutrinos mix in a very different way? These are not decorative details. They are part of the deep structure of matter. If an anomaly appears in the way beauty quarks decay into leptons, it may be pointing directly toward this unresolved family problem. A confirmed violation of lepton universality would be especially important because it would challenge one of the standard model's clean expectations. In many weak processes, electrons, muons and taus should be treated with the same underlying interaction strength once their masses and the available energy are accounted for. If a beauty meson decay truly prefers or suppresses one lepton type in a way the standard model does not allow, then something else must be present. That something could be a new particle or force. It could be a sign that lepton generations are not merely heavier copies, but are connected to deeper rules. It would tell us that the family structure of matter is not just a list of names, but a clue. This is why the possible doorway is so compelling. It does not open onto a single tidy room. It may open onto a whole hidden wing of physics. A leptoquark, for example, would directly connect quarks and leptons. That would be a major change in how we understand the separation between these particle families. It might help explain why the generations of matter repeat. It might connect flavor physics to theories that unify forces at very high energies. It might even suggest that quarks and leptons are different aspects of a larger structure. One confirmed leptoquark would not answer every question, but it would immediately change the questions physicists ask. A new heavy neutral force carrier would be just as significant in another way. It would imply an additional force of nature, perhaps one that acts mostly on certain particle generations. We are used to thinking of the fundamental forces as a small set: electromagnetism, the weak interaction, the strong interaction, and gravity, with gravity still outside the standard model's quantum framework. A new force would mean that this list is incomplete. It might be short-range and subtle, hidden from ordinary experience because it is carried by a heavy particle, or because it interacts weakly with the matter that makes atoms. But even a hidden force would alter the structure of the theory. It would give nature another way to connect particles, another rule operating beneath familiar phenomena. A hidden sector would widen the doorway even further. Dark matter already suggests that the universe contains matter unlike the atoms we know. If dark matter is not a single lonely particle but part of a broader hidden world, then that world may have its own interactions. It may communicate with ordinary matter through rare processes or faint mediators. Beauty meson decays might be one of the places where such a connection becomes visible. That idea remains speculative, but it is scientifically useful because it links separate mysteries. A small anomaly in collider data, the missing mass in galaxies, and the unexplained structure of particle generations might not be separate puzzles. They might be different edges of one larger object. Still, the doorway must be real before anyone can walk through it. This is where caution returns. Physics beyond the standard model is not a prize handed out for interesting deviations. The evidence must become strong, reproducible, and coherent. Some earlier, rare beauty decay hints involving electrons and muons have moved closer to standard model expectations with improved analysis. That is important, and it should be said clearly. The doorway did not swing open in those measurements. Some of the apparent cracks became less convincing when the experimental picture sharpened. But the wider question remains alive because other tensions, especially those involving tau leptons and related flavor observables, continue to motivate careful study. The doorway is not open. It is being tested, hinge by hinge. There is a certain discipline in accepting that. It would be easy to prefer a more dramatic story. A clean anomaly appears, a new particle is found, the textbooks are rewritten, everyone gets a very nice cup of tea. Reality is rarely so considerate. The actual frontier is messy. Results shift, uncertainties shrink, theories rise and fall. A model that looked promising one year may become strained the next. Another model may survive because it also explains a different measurement. The search beyond the standard model is not a straight road. It is a landscape of constraints, hints, false starts, and persistent questions. Yet this is exactly what makes the process reliable. Science does not move beyond the standard model by wanting to. It moves beyond it when the old model can no longer account for the evidence. That point has not been fully reached in the beauty meson story, but the search is valuable because it tells physicists where the pressure points are. Even if the anomalies fade, the improved measurements will narrow the space where new physics can hide. Even if no leptoquark appears, the absence of evidence rules out many possible versions. Even if a Z-prime boson is not found in the expected range, the constraints reshape future theories. Progress can be made by discovery, but also by careful exclusion. This is sometimes overlooked. A null result, a result that agrees with the standard model, can sound disappointing. But in particle physics, agreement can be powerful. It tells us that any new physics must be more subtle, heavier, weaker, or differently structured than certain models predicted. It sharpens the map. It removes easy paths. It prevents theorists from wandering endlessly through possibilities that nature has already rejected. The standard model surviving another test is not boring. It is the universe saying, "Not there. Try deeper." And if the anomaly survives, the consequences become far more dramatic. Suppose future data show a clear, consistent violation of lepton universality in beauty meson decays. Suppose independent measurements confirm it. Suppose related processes line up in a pattern that points toward one kind of new interaction. Then physics would have its doorway. The next step would be to identify what is behind it. Experiments would search directly for the new particle if it can be produced. Other rare decays would be measured to test the pattern. Theoretical models would become more focused. The discovery would not be the end of the story. It would be the beginning of a much larger one. The first clear sign of new physics often raises more questions than it answers. If a leptoquark were found, physicists would ask why it has its particular mass, why it couples to certain particles, whether there are more leptoquarks, and whether it belongs to a larger unified theory. If a Z-prime boson were found, they would ask what symmetry produced it, why that symmetry is hidden or broken, and what other particles must accompany it. If a hidden sector were revealed, they would ask how rich that sector is, whether it contains dark matter, and how it shaped the early universe. A doorway is exciting not because it gives a final answer, but because it proves there is more space beyond the wall. This is the deeper emotional pull of the B-meson puzzle. The standard model is beautiful, but it is also incomplete. It is like a nearly perfect machine with a few unexplained parts and a locked compartment at the back. Beauty meson decays may be one of the keys, or they may not. But they are among the rare places where the theory can be tested with enough precision to notice a very small inconsistency. The fact that such tiny particles can test such large ideas is one of the quiet marvels of physics. A meson that exists for less than a blink can ask questions about dark matter, hidden forces, particle families, and the origin of structure in nature. The doorway beyond the standard model is not only about adding more particles, it is about understanding why the known particles exist as they do. At the moment, the standard model contains many numbers that are measured rather than explained. Particle masses, mixing patterns, interaction strengths. They are built into the theory because experiments tell us their values, but the theory does not fully explain why those values are what they are. A deeper theory might reduce this arbitrariness. It might show that the masses and generations arise from a more fundamental principle. It might connect the forces. It might explain why matter survived the early universe, or it might surprise everyone by opening in a direction no one has properly imagined. This last possibility is worth keeping in mind. The history of physics is full of discoveries that did not fit the expectations of the time. The electron, the nucleus, antimatter, neutrinos, quarks, the accelerating expansion of the universe. Each one forced scientists to adjust not just their answers, but their sense of what a good question looked like. If beauty meson anomalies point beyond the standard model, the explanation may not be the simplest leptoquark or the most familiar Z-prime model. It may be something stranger. The current suspects are valuable because they are testable ideas, but nature is not obligated to choose from our first list. That is why experiments are so important. Theory can imagine many doors. Data tells us which ones have handles. LHCb and related experiments do not need to know the final theory in advance. They measure, they compare, they refine, they expose patterns that any future theory must explain. The more precise the measurements become, the less room there is for vague speculation. A real doorway must cast a measurable shadow. It must connect to other results. It must stand when the detector improves, when the dataset grows, and when independent teams ask the same question in different ways. For the moment, the doorway remains possible rather than proven. That may feel unsatisfying, but it is the honest state of the frontier. The standard model remains strong. Some earlier hints have softened. Other tensions remain under investigation. The next years of data will matter. Better measurements of beauty meson decays involving electrons, muons and taus will either close parts of the doorway or make the opening clearer. Both outcomes will teach us something. A closed door is still useful if it tells you where not to spend the night looking for ghosts. And beneath the technical details, there is a larger human theme. We have built machines that can notice the decay of particles that live for unimaginably short times. We have developed theories that predict not just what particles exist, but how often they should transform in rare ways. We have learned to treat tiny disagreements not as annoyances, but as possible clues. The doorway beyond the standard model is not a mystical place. It is the result of patience, engineering, mathematics, skepticism, and curiosity. It is built from silicon sensors, magnets, code, statistical tests, late nights, careful doubts, and the willingness to let nature answer slowly. So when we say that B-meson anomalies might open a doorway beyond the standard model, we should hear the statement in its proper scale. It does not mean the door is open. It does not mean new physics has been confirmed. It means that rare decays offer one of the most sensitive ways to test whether the known theory is complete. It means that some measurements have been interesting enough to motivate serious attention. It means that if the remaining tensions become stronger and more coherent, they could point toward particles or forces not yet known. It means that a tiny imbalance in the debris of a collision could become the first step toward a much deeper account of nature. The beauty meson does not know any of this, of course. It does not know that physicists have built detectors to catch its last traces. It does not know that theorists argue over leptoquarks, hidden forces, and flavor symmetries. It appears it travels a tiny distance and it decays. But in doing so, it gives us a rare chance to ask whether the standard model is the whole story, or only the visible surface of one. And this brings us toward the final question of the mystery. Not whether one anomaly is exciting, or whether one model is elegant, but what the universe might be trying to tell us through these small repeated tests. If the strange patterns fade, that message will be one of caution and precision. If they remain, it may be one of the first clear signs that matter has a deeper structure than we have yet understood. Either way, the beauty meson has already done something remarkable. It has turned a fleeting decay into a question large enough to reach beyond the known map. What the anomaly might be trying to tell us depends, first of all, on whether it is really an anomaly. That may sound like a cautious way to begin, but caution is not the enemy of wonder. It is what keeps wonder honest. In particle physics, the difference between a new law of nature and a temporary wrinkle in the data can be very small at first. A few more events here, a slightly better understanding of the detector there, a more careful calculation, a cleaner comparison, and the shape of the mystery can change. Something that looked like a doorway may become a shadow. Something that looked like a shadow may become the outline of a door. The work is to keep looking long enough and carefully enough to learn which is which. The beauty meson anomalies have never been a simple story of one impossible event appearing in a detector and instantly proving that the standard model is wrong. The real story is more patient than that. Certain decay patterns seemed, in some measurements, to sit away from expectation. Some comparisons involving electrons and muons once suggested that these leptons might not be appearing in the balance predicted by lepton universality. Other measurements involving heavier tau leptons have continued to draw interest because they appear difficult to fit perfectly into the expected picture. Some of the earlier electron and muon hints have softened with improved analysis. That is important. It means the evidence has changed, and science has changed with it. But the broader question remains valuable because the place where these hints appeared is one of the most sensitive places to search for physics beyond the standard model. So what might nature be saying if the remaining tensions are not accidents? One possible message is that the generations of matter are more important than we thought. The electron, the muon, and the tau are not random decorations in the particle list. They are three related particles, three charged leptons, each heavier than the last. The quarks also come in three generations. Ordinary matter around us is made mostly from the first generation, with electrons and the lightest quarks doing the everyday work of building atoms. The heavier generations appear briefly in high-energy events and particle decays. They are not common in ordinary objects, but they may be essential to understanding why the particle world has the structure it does. The standard model describes these generations with impressive accuracy, but it does not fully explain why they exist. It does not tell us why there are three of them. It does not tell us why the muon is heavier than the electron, or why the tau is heavier still. It does not give a deep reason for the pattern of quark masses, or the way quarks mix with one another. These facts are measured and placed into the theory, but they still feel like clues without the final explanation. If beauty meson decays are truly showing that different lepton generations are treated differently in ways not expected by the standard model, then perhaps the anomaly is pointing toward the hidden rule behind those generations. That would be a major step. It would mean the family structure of matter is not just a list of repeating particles, but a sign of deeper organization. The electron, muon, and tau might not simply be heavier copies of one another. They might carry different connections to unknown forces or particles. The beauty quark, sitting in an unstable meson and decaying through rare pathways, might be giving us a way to see those hidden connections. This is why the anomaly matters even when it is small. It touches one of the least understood parts of the standard model, the pattern of flavor. Flavor physics asks why particles come in different types, and how those types change. It is not as famous as the search for the Higgs boson, and it may not sound as dramatic as black holes or dark energy, but it sits close to some of the deepest open questions in particle physics. Why do particles have the masses they do? Why do they transform in some ways but not others? Why does matter dominate over antimatter? Why do neutrinos behave so differently from charged leptons? These questions are not separate boxes on a shelf. They may be connected. A small irregularity in beauty meson decays could in principle be a clue to one of those connections. Another possible message is that the weak force is not alone in shaping these decays. In the standard model, the weak interaction is responsible for many particle transformations, including the kind of quark changes involved in beauty meson decays. It has been tested extremely well, but if an unknown force also contributes even subtly, the decay probabilities could shift. The new force might be too short range to notice in everyday life. It might act mainly on heavier particles. It might couple more strongly to muons or taus than to electrons. It might not show itself directly in the detector, but it could still change the rates of rare processes. In that case, the anomaly would be saying that the known forces are not the full set of instructions. A new force would be an extraordinary discovery. It would not have to be strong in the everyday sense. It would not need to move objects across the room or make magnets behave differently on the kitchen fridge. It could be a quiet force, hidden at small distances or high energies, noticeable only when certain heavy particles decay. But even a quiet force would change the map of physics. It would mean there is an interaction in nature that the standard model does not include. It would raise new questions immediately. What particle carries this force? Why has it not been seen before? Does it connect to dark matter? Does it explain the pattern of generations? Did it matter in the early universe? A single confirmed deviation could open a long hallway of new questions. A third possible message is that quarks and leptons may be connected more directly than the standard model suggests. This is where leptoquarks become so interesting. A leptoquark would be a particle that links quarks and leptons. Since beauty meson decays involve quarks changing and leptons appearing, a leptoquark could naturally affect the process. It might prefer certain combinations such as beauty quarks and muons, or beauty quarks and taus. If it existed, it would blur a line that the standard model keeps fairly clean. It would suggest that quarks and leptons are not simply separate families that happen to share the same universe, but may be related through a deeper structure. That possibility reaches into older dreams in physics, including the hope that the different types of matter might be unified in a larger theory. For decades, physicists have wondered whether quarks and leptons are parts of a single deeper pattern. The standard model groups particles in a way that works, but it also leaves a feeling of unfinished business. The charges, masses, and generations seem arranged rather than explained. A leptoquark would not solve all of that by itself, but it would be a strong hint that the arrangement has a deeper cause. It would be like finding a passage between two rooms that everyone thought were separate. A fourth possibility is that the anomaly could be connected indirectly to the hidden matter of the universe. This is more speculative, but it is one of the reasons the story attracts wide interest. Dark matter is one of the clearest signs that known physics is incomplete. Galaxies rotate and cluster as though there is more matter present than we can see. The cosmic web has formed under the influence of this unseen mass. Yet the particles of the standard model do not provide a simple, dark matter candidate that fits everything we observe. If dark matter belongs to a hidden sector, a set of particles and forces mostly invisible to ordinary matter, then there may be rare ways for that hidden sector to communicate with the particles we know. Beauty meson decays could be one such place, not because every anomaly must be about dark matter, and not because there is proof of a connection, but because rare decays are sensitive to subtle effects. A hidden mediator, a bridge particle between ordinary matter and dark matter, might change decay rates or produce missing energy. It might prefer heavier generations. It might appear only through small distortions in processes that are already rare. If that were true, a tiny imbalance in the behavior of beauty mesons could be related to the much larger mystery of why galaxies hold together as they do. That is a big leap, and it remains only a possibility, but physics often advances by testing whether distant puzzles share a common root. There is also a simpler message the anomaly might be trying to tell us. It might be saying that the standard model is even more resilient than we thought. If future measurements show that the remaining tensions fade, that would not be meaningless. It would mean that nature follows the known rules in this area with even greater precision. It would mean that some proposed new particles are more tightly constrained or ruled out. It would mean that the search must move elsewhere, or become more sensitive, or ask the question in a different way. A disappearing anomaly can feel disappointing, but it strengthens the foundation by showing where the cracks are not. This is something worth remembering. Science does not only progress when a new particle is found, it also progresses when an old suspicion is tested and dismissed. If an apparent deviation turns out to be a statistical fluctuation, physicists learn how easily chance can imitate meaning. If it turns out to be a measurement issue, they learn how to improve the experiment. If it turns out to be a difficult standard model effect, they learn more about the theory they already have. Every outcome teaches something. The only failure would be to stop asking before the answer is clear. The beauty meson puzzle is therefore not just a hunt for new physics. It is a test of how modern physics works at the edge of knowledge. It shows that discovery does not usually arrive as a single clean surprise. It arrives as a conversation between theory and experiment. The experiment measures a decay. The theory predicts a rate. The result does not quite match. The theorists propose explanations. The experimentalists gather more data. The theorists check whether their models survive other constraints. The experiment improves. Some ideas fall away, some measurements shift, the process repeats. It is slow, careful, and sometimes frustrating, but it is the reason the final answer can be trusted. If the anomaly is real, one thing it may be telling us is that small particles can reveal large structures. A beauty meson is temporary. It exists for a time so short that the word brief seems too large. It travels a tiny distance and decays, yet that tiny event can test principles that reach across all of particle physics. It can test whether leptons are treated universally. It can test whether hidden particles influence rare processes. It can test whether the generations of matter are connected by rules we have not yet discovered. The scale of the particle is small, but the question it asks is not. That is one of the strange gifts of high-energy physics. The deeper we look into matter, the more the universe seems to connect the very small with the very large. Particles created in underground collisions may help explain the early universe. Rare decays may point toward dark matter. Tiny imbalances may reveal broken symmetries. A short-lived meson may challenge a theory that describes almost everything we have measured in the particle world. The size of the clue does not determine the size of the truth behind it. For now, the careful answer is that the anomaly has not spoken clearly enough. It has hinted, it has shifted, it has partly softened, it has left some questions behind. Future data from LHCb and other experiments will decide whether those questions become sharper or fade away. More beauty meson decays will be recorded. More tau channels will be studied. More electron and muon comparisons will be made. The upgraded detector will improve sensitivity. Theoretical calculations will continue to refine the standard model expectations. The suspects will remain under watch. Leptoquarks, Z-prime bosons, hidden forces, dark sector mediators, extended Higgs particles, and other possibilities will either find support or be pushed into smaller and smaller corners. There is no need to rush that process. In fact, rushing would spoil it. A premature claim would not bring us closer to truth. It would only make the fog louder. The right answer will come from consistency. If new physics is there, it should show up in more than one way. It should form a pattern across different decays and experiments. It should survive improved measurements. It should not depend on one fragile irregularity. Nature can be subtle, but it is not usually careless. A real new law leaves more than one footprint, and if the footprint is real, then the message may be that the standard model is a surface layer, a very good surface layer but not the deepest one. Beneath it may be another structure that explains why matter has generations, why forces act as they do, and why some particles seem to carry hidden relationships. That deeper structure may be elegant, or it may be stranger than current theories expect. It may involve particles we have named but not found, or particles no one has yet imagined properly. It may connect to dark matter, or to the early universe, or to a symmetry that is broken in a way we have not yet understood. The most honest thing to say is that we do not know yet, but we know where to look. That is not a small achievement. For a theory as successful as the standard model, finding any place where new physics might enter is difficult. The obvious doors have often been checked. Many expected signals have not appeared. The absence of new particles in direct searches has made the hidden possibilities more important. Rare decays, precision measurements, and tiny anomalies have become some of the best tools we have. The beauty meson is one of those tools. It is not dramatic by itself, but it is sensitive. It can feel the pressure of particles too heavy or too hidden to be seen directly. So perhaps the anomaly is telling us to pay attention to flavor, to the differences between particle generations, to the possibility that the muon and tau are not merely heavier versions of the electron, but clues to a deeper layer. Perhaps it is telling us that the road beyond the standard model will not begin with a giant new particle appearing all at once, but with a slight imbalance in a rare decay. Perhaps it is telling us that nature hides its next secret not in a loud collision, but in a comparison between outcomes that should have matched. Or perhaps it is telling us something humbler, that the known theory still works, that our instruments must become better, that rare decays are difficult, that patience is part of discovery. This would not be a disappointing message. It would be a reminder that the universe is not required to satisfy our appetite for novelty. The Standard Model has earned every one of its victories, and if it wins again here, physicists will accept that and keep searching elsewhere. Either way, the beauty meson has already served its purpose. It has made physicists ask a sharper question. It has drawn attention to the hidden structure of particle families. It has forced theories beyond the Standard Model to become more precise. It has shown the value of detectors built not only to find big new objects, but to measure delicate differences. It has reminded us that science is often less like breaking down a wall and more like noticing that one brick is slightly warmer than the others. And now, after following the beauty meson from its brief birth in a collider collision to its rare decays, from electrons and muons to possible hidden forces, from cautious measurements to large unanswered questions, we can let the mystery rest where it belongs, not solved, not forgotten, but carefully held. Somewhere beneath the ground near Geneva, the detectors continue their work. Protons collide, beauty particles appear and vanish, tracks curve through magnetic fields, electrons shower, muons pass through, taus decay before they can be held for long. Computers collect the traces, and physicists turn those traces into questions. Maybe the answer will be ordinary. Maybe it will be extraordinary. Maybe the next round of data will close this particular doorway. Maybe it will open it wider. For tonight, it is enough to understand why the question matters. A tiny particle may be pointing toward a hidden rule. A rare decay may be testing the fairness of the weak force. A small mismatch may be a clue to a larger theory. And even if the whisper fades, the listening has not been wasted. So as the day softens, and the mind begins to loosen its grip on the details, let the scale of the story settle gently. We are made of ordinary matter, mostly first-generation particles, stable enough to form atoms, cells, thoughts, and sleepy questions at the edge of night. Yet to understand why that ordinary matter exists, we must study particles that vanish almost as soon as they are born. We must build machines beneath the earth to catch their traces. We must compare electrons with muons, taus with expectations, and rare decays with the rules of a theory that is both magnificent and unfinished. If there is something beyond the Standard Model, it may not announce itself loudly. It may arrive as a small difference checked again and again. It may wait inside the decay of a beauty meson, in a number that refuses to settle, in a pattern that becomes clearer only after years of patient work. And if that happens, then the anomaly will have been trying to tell us something simple and profound. The universe still has more structure than we know. For now, the detectors keep listening, the data keep gathering, the Standard Model keeps standing. And somewhere in the quiet space between what is measured and what is understood, physics continues, one rare decay at a time.